The strangest thing about the ancient world may be what is missing. The machines are gone. The construction plans are gone. In many places, even the names of the people responsible have disappeared. Yet their work remains. Vast foundations beneath living cities, monuments cut into mountains, complex water systems, enormous walls, and structures positioned with extraordinary precision. We see the finished result without witnessing the process that made it possible. Like arriving at the final scene of a story whose opening chapters have been torn away. Archaeology continues to recover those missing pages, one discovery at a time. But some gaps refuse to close, leaving behind places where evidence ends, certainty disappears, and one of the most fascinating sides of the ancient world begins. Vindolanda, Northumberland, Northern England. A Roman frontier fort buried in wet earth, just south of Hadrian's Wall. It was not discovered as a single lost city. It emerged slowly, layer by layer, through excavations that revealed one of the strangest archives of the Roman world. Wood, leather, ink, and ordinary voices surviving almost 2,000 years underground. Vindolanda was occupied from roughly AD 85 to AD 370, guarding the Stanigate Road before and during the age of Hadrian's Wall. What makes Vindolanda mysterious is not a giant temple or a vanished king. It is something smaller, thinner, and more fragile. Wafer-like wooden tablets, some only millimeters thick, carrying handwritten Latin from the edge of the empire. The British Museum explains that these tablets survived because many Vindolanda deposits were waterlogged, creating anaerobic conditions where oxygen-hungry bacteria could not destroy organic material. In the same sealed layers, archaeologists found leather shoes, wooden objects, and even rare personal items that normally disappear from the archaeological record. The first great shock came in 1973, when excavations led by Robin Burley revealed thin wooden writing tablets in the damp early fort levels. Before that, Roman ink writing on wood was not expected to survive in Britain. The tablets were not monumental inscriptions carved for public memory. They were working documents, letters, lists, orders, requests, accounts, and personal messages. More than 1,700 tablets have now been discovered, dating mainly to the late 1st and early 2nd centuries AD. The deepest technical puzzle begins with the tablets themselves. They were not heavy wax boards. They were thin wooden leaf tablets, made from woods such as birch, alder, and oak, written in carbon-based ink. Some were roughly postcard-sized, others were broken fragments. Their surfaces had to be smooth enough to take ink, thin enough to fold or carry, but strong enough not to split during use. That combination is difficult. Wood moves with moisture. It warps, curls, cracks, and separates along the grain. Yet the Roman frontier office system used these objects as everyday stationery. This raises an unresolved technological question. How were so many ultra-thin writing boards produced with such consistency? A tablet only a few millimeters thick is not easy to cut from green wood with hand tools. If it is shaved too early, it bends as it dries. If it is shaved too late, the surface can tear. If the grain is wrong, the ink spreads or the sheet breaks. The surviving tablets suggest a craft process that was more controlled than simple camp improvisation. Someone knew which tree species worked, how to split or plane the wood, how to prepare the surface, and how to make a writing material cheap enough for daily use on a remote military frontier. The mystery is not that Romans could cut wood. The mystery is the scale and reliability. Vindolanda was not Rome, Alexandria, or a wealthy Mediterranean port. It stood near the northern limit of Roman Britain, in a cold and wet landscape. Yet its officers and households had access to a writing system that functioned like a disposable paper economy before paper became common in Europe. Every request for beer, socks, grain, hides, or leave depended on a chain of materials: trees selected, boards prepared, ink made, pens cut, messages delivered, and records stored or discarded. The tablets reveal not only literacy, but a hidden manufacturing network. The ink itself adds another layer. The writing was made with carbon-based ink, not scratched letters in wax. Carbon ink needs a fine pigment, a liquid binder, and a stable suspension. Too watery, and it bleeds into the wood. Too thick, and it clogs the pen. The writing on many tablets is faint today, but originally it had to be readable to soldiers, clerks, traders, and commanders. That means the Roman frontier possessed a practical chemistry of writing. Charcoal or soot reduced to fine particles, mixed with binding agents, carried in containers, and used in an environment where rain and damp were constant threats. Even more strange is the survival of the ink. Organic materials decay quickly, and ink on wood should be among the first traces to vanish. At Vindolanda, preservation depended on a precise accident of soil and water. The Vindolanda Trust describes the anaerobic layers as waterlogged deposits created by a rising water table, where objects were almost deprived of oxygen and bacterial activity was very low. But this creates a paradox. The same dampness that normally destroys writing helped protect it. The tablets survived because they were buried in a chemical world where decay slowed almost to a stop. That environment was not planned as a library. It was the result of rebuilding. The early wooden forts at Vindolanda were repeatedly demolished, leveled, sealed, and built over. Floors, rubbish, timber, leather, straw, and clay became compact layers. Over time, the lower deposits turned into an oxygen-poor chamber. It is as if a frontier base accidentally engineered a time capsule. The Roman army did not mean to preserve its paperwork for 2 millennia, yet its construction habits helped create the conditions that saved it. The tablets also expose a second technological mystery: administration at the edge of empire. Many ancient armies could fight. Fewer could count, record, supply, and communicate across vast distances with this level of routine detail. Vindolanda's texts mention military matters and personal affairs, including correspondence linked to Flavius Cerealis, prefect of the 9th cohort of Batavians, and his wife Sulpicia Lepidina. The famous birthday invitation from Claudia Severa to Lepidina, around AD 100, is among the earliest known examples of Latin writing by a woman. These are not just touching human details, they prove that writing technology was embedded in daily logistics. A frontier commander could receive supply notes. A household could send invitations. Traders could discuss wheat, hides, and sinews. Soldiers could ask for clothing. The tablets show a military society held together by messages. The unanswered question is how standardized this system really was across the empire. Vindolanda survived because of rare soil. Other forts may have produced similar archives that simply rotted away. The organic finds deepen the puzzle. Vindolanda has yielded thousands of leather shoes and other leather objects, preserved in the same oxygen-poor deposits. Some collections number around 5,000 shoes, including baby shoes, sandals, and military footwear. This is evidence for families, workers, soldiers, and children living around a supposedly military zone. It also points to a huge leather economy: tanning, cutting, stitching, repairing, and recycling on a scale that is still difficult to reconstruct. Leather is technically demanding. It requires animal supply, curing, tanning agents, skilled labor, and waterproofing. A northern frontier fort needed shoes that could survive mud, marching, and cold weather. The many styles found at Vindolanda suggest not crude mass footwear, but adapted products for status, age, function, and environment. If leather items were produced locally, then the frontier had specialized workshops. If they were imported, then the Roman supply network was more efficient than the physical ruins alone suggest. Either answer implies a sophisticated industrial rhythm behind everyday objects. The same can be said of timber construction. Vindolanda's earliest forts were built largely in wood before later stone phases. Wood is fast, flexible, and abundant, but it is also vulnerable. To build barracks, gates, drains, floors, and storage areas in a wet frontier landscape required practical engineering. The repeated rebuilding of the site left behind compacted layers that later became archaeologically priceless. What appears as military routine may have created a layered ground system that controlled water, supported buildings, and sealed rubbish in stable deposits. In the heart of Shiraz, Iran, a brick fortress rises like a sealed machine from the Zand dynasty. Aghe Karim Khan was not discovered beneath desert sand. It survived in plain sight, in the center of Shiraz, later reused as a prison, restored as a monument, and studied as one of the largest brick structures of the Zand architectural complex. Historical sources place its construction around 1766 to 1767, when Karim Khan Zand made Shiraz his capital. Its plan is almost brutally simple: a rectangular citadel about 124.8 meters east to west and 93.6 meters north to south, protected by walls roughly 12 meters high and corner towers reaching about 15 meters. Yet the closer engineers look at it, the less simple it becomes. The first puzzle is the contradiction between mass and survival. Aghe Karim Khan is built mainly from fired brick, with walls reported to be around 3 meters thick at the base and 4 circular corner towers, locking the corners into a defensive geometry. Brick masonry performs beautifully under compression, but it is vulnerable to tension, lateral shaking, foundation movement, moisture, and salt crystallization. Iran is one of the world's most seismically active regions, and traditional masonry vaults, domes, and walls are known to be vulnerable under earthquake loading. Yet this citadel has remained standing for more than 2.5 centuries. Its survival is not magic, it is engineering. But the exact engineering logic behind that survival has never been completely reconstructed. The deepest mystery may be hidden in the joints between the bricks. Traditional Persian builders did not rely on modern cement. They used lime-based mortars, clay-rich mixtures, gypsum compounds, and in some regions, a hydraulic mortar known as saruj. Scientific reviews describe saruj as an ancient Persian lime mortar, often involving hydrated lime, ash, or pozzolanic material, sand, clay, and water. One reported experimental mix used 10 parts hydrated lime, 7 parts fly ash, 1 part sand, 1 part clay, and 7 parts water by volume. But that recipe is not necessarily the exact formula used at Aghe Karim Khan. It only reveals the larger mystery. Persian builders possessed a practical materials science that was never fully written down. What makes this mortar mystery so important is that lime mortar is not just glue. It breathes, absorbs movement, releases moisture, and slowly gains strength through carbonation. When mixed with pozzolanic additives, it can even develop hydraulic properties, meaning it can harden in damp conditions. Conservation studies on historic mortars show that mortar composition varies widely. and that lime mixed with reactive additives can behave very differently from ordinary non-hydraulic lime. This means the unknown formula at Arg-e-Karimkan may have helped the fortress survive cycles of heat, winter cold, moisture, salt, and structural movement without cracking apart like a rigid cement shell. The lost knowledge was probably not a single ingredient, but a process. Builders had to choose the lime, burn it correctly, slake it safely, age it, blend it with ash, clay, crushed brick, sand, or organic additives, then apply it at the right moisture level. A small change in firing temperature, grain size, curing time, or water ratio could transform the behavior of the entire wall. Modern researchers can identify calcium compounds, silicates, alumina, pores, and mineral phases, but chemical analysis does not automatically recover the hands of the craftsman. The real secret was not only what they mixed, it was how long they waited, how they judged texture, how they controlled drying, and how they matched mortar strength to brick strength. That last point is crucial. A strong mortar is not always a good mortar. In historic brickwork, the joint must often be softer and more sacrificial than the brick. If the mortar is too rigid, stress concentrates inside the bricks and destroys them. If it is too weak, the wall separates. Argi-Karimkan appears to have reached a careful balance between stiffness and flexibility. This may explain why modern cement repairs can be dangerous in old masonry. Portland cement can trap moisture, create salt pressure, and behave too rigidly beside older materials. The citadel's original builders seem to have understood compatibility by experience, long before modern conservation science gave that principle a name. The brickwork itself raises another technical question. A fortress of this size required vast quantities of fired brick, with consistent dimensions and firing quality. The walls, towers, vaults, and decorative surfaces could not have been built with random material. The bricks had to be shaped, dried, fired, sorted, transported, and laid in a controlled sequence. The citadel's scale suggests a near-industrial supply chain operating in 18th century Shiraz. Clay extraction, kiln management, fuel supply, water access, labor organization, and quality control. The kilns that produced this material are not as famous as the citadel itself, yet they may be the invisible factories behind the monument. Then there is the strange problem of the Leaning Tower. One of the corner towers of Argi-Karimkan is visibly tilted, often compared by visitors to a small Persian echo of Pisa. But the more interesting fact is not that it leans. The more interesting fact is that the surrounding structure did not catastrophically fail. A leaning masonry tower creates eccentric loading, uneven compression, and dangerous shear stresses at its base. In a rigid structure, this can trigger progressive cracking. At Argi-Karimkan, the thick walls, circular tower geometry, gradual settlement, and flexible lime-based joints may have redistributed forces over time. The tower became deformed, but the system did not collapse. This points toward a larger foundation mystery. Shiraz sits in an environment where soil moisture, seasonal change, and urban development can affect buried foundations. Arg-e-Karimkan's builders had to support immense brick mass without reinforced concrete, steel piles, or modern soil testing. They may have relied on compacted layers, broad footings, rubble packing, drainage logic, or traditional knowledge of local ground behavior. But without full excavation beneath the walls, the foundation system remains partly unknown. The visible building tells us that the solution worked. It does not tell us exactly how it was made. Inside the citadel, the mystery changes from mass to geometry. Persian architecture made wide use of arches, vaults, and domes, because masonry is strongest when forces move through compression. Studies of traditional masonry arches and vaults show that these forms can span large spaces without modern beams, but they are also sensitive to support movement and lateral forces. At Arge Karim Khan, rooms and corridors use vaulted forms that convert gravity into controlled thrust. The thick walls are not just defensive barriers, they are structural receivers, absorbing the outward push of the vaults. This geometry required more than artistic tradition. Builders needed centering systems, bricklaying sequences, curvature control, and an intuitive understanding of thrust lines. A vault can stand for centuries if its compression path remains inside the masonry. If that path shifts too far, cracks open and collapse begins. The unanswered question is how Zand-era builders checked these geometries on site. Did they use templates, ropes, wooden guides? Proportional rules inherited from older Persian architecture? No complete construction manual survives for this specific project. The citadel preserves the result, but not the calculation. Arg-e-Karim Khan also behaves like a climate machine. Shiraz can experience intense summer heat, yet the fortress uses thick masonry, shaded rooms, limited openings, and a central courtyard to moderate temperature. Heavy brick walls store heat slowly, delaying the movement of outdoor temperature into interior space. Courtyards can create pressure differences and shaded air circulation. In traditional Iranian architecture, these passive strategies often reduced heat without mechanical systems. At the citadel, this climate control was not separate from structure. The same thick walls that resisted attack also stabilized indoor temperature. What do you think was the true secret behind Argi-Karim Khan's survival? The lost mortar recipe, the brickwork, or the builder's forgotten engineering knowledge? Share your thoughts in the comments below. Located along the Danube in northern Bulgaria, Oescus preserves one of the Roman world's most overlooked engineering mysteries, where mosaics, concrete, hydraulic systems, and the remains of an enormous bridge continue to challenge modern archaeological science. Oescus is an ancient Roman city located near today's village of Gigan in northern Bulgaria, approximately 5 kilometers south of the Danube River. Originally established beside a Thracian settlement, it became the permanent base of Legio V Macedonica during the 1st century AD, before Emperor Trajan elevated it to the status of a Roman colonia around AD 106. Although the site had attracted antiquarian attention for centuries, systematic archaeological excavations only began during the early 20th century and expanded significantly after the 1940s, revealing forums, baths, temples, workshops, streets, residential quarters, water infrastructure, and some of the finest Roman mosaics discovered anywhere in the Balkans. Excavated remains now cover more than 100,000 square meters, yet this represents only part of a city that once occupied several dozen hectares. Among everything uncovered at Oescus, the House of Fortuna has generated perhaps the greatest technological puzzle because its extraordinary mosaic floors remain remarkably well preserved after nearly 17 centuries, despite exposure to earthquakes, seasonal flooding, changing groundwater conditions, and long periods of abandonment. The largest surviving composition depicts the goddess Fortuna, surrounded by geometric borders, birds, floral ornaments, and carefully arranged colored tesserae cut from limestone, marble, ceramic, and colored glass. Archaeologists estimate that individual mosaics contain hundreds of thousands of tiny pieces, many measuring only 1 to 2 centimeters across, each positioned with astonishing precision to create smooth transitions of color and perspective. Scientific analyses using petrographic microscopy, X-ray diffraction, and scanning electron microscopy have shown that the durability of these floors depends not only on the visible stones, but also on the sophisticated multi-layer foundation beneath them. Roman builders first created a compact stone base known as the statumen, followed by a thick rudous layer of crushed stone mixed with lime mortar, then a finer nucleus composed of lime, sand, and carefully graded aggregates, before finally placing the tesserae into a thin bedding layer. This layered structure distributed mechanical stress while allowing slight movement without causing widespread cracking, explaining why large sections remain almost perfectly level after more than 1,600 years. Yet the greatest mystery lies inside the mortar itself. Modern laboratory studies consistently identify calcium carbonate crystals, hydrated lime products, and microscopic mineral bonds that continue to strengthen over time through slow chemical reactions with groundwater and atmospheric carbon dioxide. Similar self-healing behavior has recently been documented in several Roman mortars across the Mediterranean, where dissolved calcium can recrystallize inside microscopic fractures, naturally sealing tiny cracks before they expand into structural failures. At Oescus, however, researchers still cannot reconstruct the precise mixture that produced these exceptionally durable foundations, because no written construction manuals survive for this specific workshop. The proportions of lime, water, aggregate, firing temperature, curing period, and local mineral additives remain uncertain, while even slight changes in these variables could significantly alter the long-term performance of the material. Equally remarkable is the stability of the pigments. Red tones produced from iron-rich minerals, black from carbon-based materials, white from marble, green from copper-bearing minerals, and colored glass tesserae have retained much of their original appearance despite nearly 2 millennia of oxidation, moisture, biological growth, and temperature fluctuations. Scientists understand the mineral sources of these colors, yet the complete production process that allowed them to resist fading so effectively is still only partially understood. The engineering sophistication visible beneath these decorative floors naturally raises broader questions about the city itself. Oescus stood on the floodplain of one of Europe's largest rivers, where unstable alluvial sediments, seasonal flooding, and fluctuating groundwater would normally threaten heavy masonry construction. Excavations nevertheless reveal buildings whose foundations remain remarkably stable after centuries of environmental change. Beneath many structures, archaeologists identified carefully prepared sequences of gravel, compacted stone, sand, and lime mortar, arranged to improve drainage and spread structural loads. Modern geotechnical engineering follows similar principles, but Roman builders possessed neither mechanical drilling equipment nor mathematical soil models. The archaeological record demonstrates that they understood local ground behavior well enough to support temples, administrative buildings, bath complexes, and large residential houses, although exactly how they evaluated soil stability before construction remains unknown. That understanding extended into water management, another field in which Oescus demonstrates remarkable technical competence. Excavations have uncovered aqueducts, underground drains, reservoirs, distribution channels, and lead pipelines supplying baths, fountains, and private residences. Because the surrounding terrain lacks the dramatic elevation changes seen in many other Roman cities, engineers had to maintain extremely precise hydraulic gradients to keep water flowing efficiently while avoiding excessive pressure that could damage pipes. Sections of surviving conduits reveal carefully controlled slopes over considerable distances, suggesting detailed surveying before construction began. Roman instruments such as the groma, corobats, and dioptra are known from historical sources, yet archaeologists still debate how surveyors consistently achieved such accuracy across an expanding urban landscape, using only these relatively simple devices. The city's structural materials present another unanswered question. Walls throughout Oescus were constructed using combinations of fired brick, limestone blocks, and opus caementicium, the famous Roman concrete whose long-term durability continues to attract scientific attention. Laboratory investigations of Roman concrete from numerous Mediterranean sites have identified rare calcium-aluminum silicate hydrate phases, together with lime clasts capable of promoting limited self-repair when cracks develop. Although Oescus does not preserve concrete on the monumental scale seen at Roman harbors, surviving masonry demonstrates comparable resistance to weathering. Researchers still cannot determine whether local builders imported volcanic materials from distant regions, relied entirely on local aggregates, or modified traditional Roman recipes to suit the geology of the lower Danube. The greatest engineering achievement associated with Oescus once extended far beyond the city walls. In AD 328, Emperor Constantine inaugurated an enormous bridge linking Oescus with Suceava on the opposite bank of the Danube. Ancient sources attribute the design to the engineer Theophilus Patricius and describe a structure approximately 2.5 kilometers long, with roughly 1.3 kilometers crossing the river itself, making it one of the longest bridges ever built in the Roman world. Constructing such a crossing required foundations capable of resisting powerful currents, drifting ice, seasonal floods, and unstable river sediments. Only fragments of foundations and scattered archaeological evidence survive today, leaving historians unable to reconstruct the complete construction sequence. Massive cofferdams, timber piles, lifting systems, cranes, and coordinated labor must all have played essential roles, yet almost every temporary engineering solution disappeared once the bridge was completed, leaving the finished monument but not the methods that created it. Ajanta caves remained hidden beneath dense jungle in the Sahyadri hills of Maharashtra, Western India, until British officer John Smith accidentally encountered the site while hunting in 1818. Cut into a horseshoe-shaped basalt cliff overlooking the Waghora River, the complex contains 30 rock-cut caves created between the 2nd century BCE and approximately the 6th century CE. At first glance, Ajanta appears to be another remarkable Buddhist sanctuary, yet modern geological surveys, laser documentation, structural analyses, and archaeological research reveal a far deeper engineering mystery. The greatest question is not who carved these monuments, but how an entire mountainside could be hollowed into vast halls without triggering catastrophic collapse, allowing the complex to survive more than 2,000 years despite monsoon rains, weathering, groundwater infiltration, and repeated geological stress. What immediately separates Ajanta from most ancient monuments is that nothing was assembled. Every column, ceiling, staircase, shrine, corridor, doorway, and sculpture was created by removing rock from a single cliff, rather than transporting building materials into place. Archaeologists estimate that tens of thousands of cubic meters of basalt were excavated throughout the construction of the complex. Unlike masonry architecture, where mistakes can often be corrected by replacing damaged blocks, every strike of the hammer permanently removed part of the mountain. A single error in determining roof thickness or cutting direction could have destroyed months or even years of work by causing fractures to spread through the remaining rock. Yet the largest prayer halls still retain roofs spanning nearly 15 meters in height and almost 30 meters in length, with remarkably little structural deformation. This achievement becomes even more difficult to explain when considering the geology of the Deccan Traps, one of the largest volcanic provinces on Earth. Formed by enormous basaltic eruptions around 66 million years ago, these lava flows cooled into successive layers, separated by joints, fractures, and weathered zones. Basalt appears visually solid, but its internal strength varies significantly depending on cooling history, mineral composition, and natural cracking. Modern engineers normally rely on drilling cores, seismic imaging, and laboratory testing before excavating large underground chambers within volcanic rock. The builders of Ajanta possessed none of these technologies, yet they consistently selected portions of the cliff capable of supporting immense cavities, while apparently avoiding the weakest geological zones. No surviving inscription explains how they identified stable rock before excavation began. As researchers reconstructed the carving sequence, another mystery gradually emerged. Physical evidence preserved on unfinished surfaces indicates that excavation generally progressed from the top downward rather than from the entrance inward. Workers first established the roof, then gradually descended through the interior until columns, walls, and floors finally emerged from the remaining stone. Such a method required every important structural decision to be made before the surrounding material had even been removed. Builders had to predict the final dimensions of chambers while standing inside solid rock, leaving virtually no possibility of correcting errors once excavation advanced. Even today, underground engineering projects depend heavily on continuous monitoring, because the removal of rock constantly redistributes stress throughout the surrounding mass. Ajanta's creators somehow managed this process across multiple generations without written engineering manuals that have survived. The stone columns themselves deepen the puzzle. Visitors naturally admire their elaborate capitals, carved figures, and decorative symmetry, yet structural engineers increasingly view them as integral load-bearing elements rather than purely artistic features. In several caves, the spacing between columns subtly changes instead of following perfectly uniform intervals. Some stand slightly closer together near wider roof spans, while others align with natural variations in the surrounding rock. These adjustments are often measured only in centimeters, but they influence how compressive forces travel through the remaining basalt. Whether these placements resulted from practical observation accumulated through experience or from a sophisticated understanding of rock mechanics remains impossible to determine, because the technical knowledge behind these decisions disappeared long ago while the stone itself continued carrying the load. Attention has also focused on the remarkable condition of the ceilings. Across more than 20 centuries, the caves have experienced countless monsoon seasons capable of delivering well over 2,000 millimeters of annual rainfall in parts of the region. Water is among the greatest enemies of rock-cut architecture because it penetrates fractures, dissolves weaker minerals, expands existing cracks through repeated wetting and drying cycles, and encourages vegetation whose roots exert tremendous mechanical pressure. Nevertheless, large sections of Ajanta remain structurally intact. Geological investigations have documented localized weathering and surface deterioration, but widespread roof failure never occurred. This unexpected durability suggests that ancient builders deliberately preserved sufficient roof thickness while exploiting the strongest portions of each basalt layer, although the precise criteria guiding those decisions remain unknown. Evidence surrounding the cave entrances suggests another overlooked engineering strategy. Rather than allowing seasonal runoff to flow directly across carved facades, many sections of the cliff incorporate carefully shaped channels and overhangs that redirect water away from vulnerable openings. Even subtle changes in rock geometry reduce the amount of water penetrating interior chambers. Modern conservation teams continue managing drainage because uncontrolled infiltration remains the greatest threat to the caves today. The fact that ancient excavators recognized this danger centuries before modern geology existed indicates that they possessed a sophisticated empirical understanding of long-term environmental processes, developed entirely through observation rather than formal scientific theory. The precision achieved across the interiors raises additional questions. Laser surveys have demonstrated that many ceilings, walls, and corridors remain strikingly regular despite having been carved entirely by hand. Long axial corridors maintain consistent alignment over considerable distances, while broad ceiling surfaces show only minimal deviation from their intended geometry. Such accuracy becomes especially remarkable considering that excavation occurred inside enclosed spaces illuminated only by oil lamps or reflected daylight entering from the facade. Every measurement had to be transferred manually, without electronic instruments, optical levels, or precision laser references. Even slight directional errors introduced early in excavation would have become increasingly magnified as work progressed deeper into the mountain. Yet the finished architecture displays a consistency difficult to reconcile with the technological limitations of the period. The famous Chaitya prayer halls introduce another phenomenon that continues attracting scientific interest. Their barrel-vaulted ceilings, apsidal plans, and carefully proportioned interior volumes generate unusually effective acoustics. Modern acoustic measurements have shown that chanting spreads evenly through these spaces, while limiting excessive echo that would otherwise reduce speech intelligibility. Curved ceilings reflect sound toward occupied areas rather than dispersing it randomly, producing reverberation characteristics well suited to ritual recitation. No ancient document attributes these properties to deliberate acoustic design, yet the geometry repeatedly achieves results that modern architects often model digitally before construction. Whether these effects emerged through centuries of experimentation or through intuitive refinement remains unresolved. Beyond the structural questions, Ajanta preserves one of humanity's most extraordinary collections of ancient mural painting. Created over several centuries, the paintings survive because artists first prepared the volcanic rock with multiple layers of clay, lime, organic fibers, and fine plaster before applying mineral pigments derived from natural sources such as red ochre, yellow ochre, carbon black, kaolin, and imported lapis-based blue in limited areas. Scientific analyses using microscopy, spectroscopy, and chemical characterization have shown that the painters carefully controlled both surface preparation and pigment composition to maximize durability. Even so, conservators still debate why certain sections retained exceptional color stability despite fluctuations in humidity, seasonal temperature changes, biological growth, and centuries of neglect after the caves were abandoned. Perched above the city of Cusco in the Peruvian Andes at an elevation of approximately 3,700 meters, Sacsayhuaman is a fortress whose massive stone walls appear to defy one of nature's most destructive forces. More than 5 centuries after the arrival of the Spanish, and despite repeated powerful earthquakes in one of South America's most active seismic regions, its towering terraces remain standing where many younger structures have repeatedly failed. Unlike Machu Picchu, Sacsayhuaman was never truly lost. Spanish chroniclers, including Pedro Cieza de León, described the fortress shortly after the conquest of the Inca Empire in the 16th century, although much of its finely cut stone was later dismantled and reused to construct colonial buildings throughout Cusco. Even after centuries of quarrying, enough of the original structure survived for archaeologists and engineers to recognize that the remaining walls represented one of the most extraordinary examples of prehistoric stone engineering ever built. The greatest mystery is not how large the stones are, but why the walls have refused to collapse. Cusco lies within the active Andean seismic belt, created by the ongoing subduction of the Nazca Plate beneath the South American Plate, a tectonic process occurring at roughly 7 to 8 centimeters per year. This region has experienced numerous destructive earthquakes throughout recorded history, including major events in 1650, 1950, and many smaller earthquakes that continuously subject ancient structures to repeated cycles of ground motion. Colonial churches, masonry buildings bonded with mortar, and later stone constructions have all suffered severe damage or complete collapse during these events. Yet the polygonal walls of Sacsayhuaman remain remarkably intact. For structural engineers, this represents the site's most remarkable achievement, because the walls appear to survive precisely by doing what conventional masonry should never do. Instead of resisting earthquakes as rigid bodies, they seem to move with them. Modern structural analyses suggest that each stone functions as an independent structural element, capable of minute movement during seismic shaking. Rather than transferring stress directly through continuous mortar joints, the dry-fitted blocks distribute seismic energy across hundreds of irregular contact surfaces. Small displacements measured in millimeters allow the blocks to absorb energy before gravity guides them back into position once the shaking subsides. This principle resembles modern seismic isolation concepts, although it was achieved entirely through geometry rather than engineered bearings or synthetic materials. Numerical modeling published by engineering researchers has shown that irregular polygonal joints reduce stress concentrations that normally develop along straight vertical mortar seams, making crack propagation significantly more difficult during cyclic loading. Whether Inca builders fully understood these mechanical principles remains impossible to prove, yet the performance of the walls over centuries strongly suggests an empirical mastery of earthquake-resistant construction unmatched anywhere else in the pre-Columbian Americas. The geometry of the masonry only deepens the mystery. Unlike conventional walls built from standardized rectangular blocks, almost every visible stone at Sacsayhuaman possesses a completely unique outline. Many blocks contain 10, 12, or even more than 15 precisely shaped faces that interlock with neighboring stones in multiple directions simultaneously. The contact surfaces are so accurately fitted that even today many joints remain only a few millimeters wide, despite centuries of weathering. The fortress was primarily constructed from extremely hard andesite, an igneous rock considerably more difficult to shape than the limestone used for many ancient monuments elsewhere. Experimental archaeology has demonstrated that andesite can be worked using harder stone hammers and abrasive techniques, yet reproducing the same level of precision across hundreds of irregular multi-ton blocks remains extraordinarily labor-intensive. No surviving Inca documents explain how templates, measurements, or fitting sequences were organized, leaving the entire production process largely reconstructed through inference rather than direct evidence. The enormous size of the stones creates another engineering puzzle. The largest surviving blocks are commonly estimated to weigh between 100 and 150 tons, while some researchers have proposed values approaching 200 tons for the largest examples depending on volume calculations and rock density. These stones stand on steep mountain terrain without reinforced concrete foundations, steel anchors, or deep piles. Geological surveys indicate that many sections were placed directly upon carefully prepared natural bedrock, rather than artificial platforms. By anchoring the walls to stable rock instead of relying on thick masonry foundations, Inca engineers reduced differential settlement while allowing the structure to behave as part of the underlying mountain itself. The result is a foundation system that has remained stable despite centuries of seismic activity and seasonal environmental change. The famous zigzag layout of the three defensive terraces may also represent more than military architecture. Historians traditionally interpret the repeated angles as a method for creating overlapping defensive positions from which defenders could attack advancing enemies from multiple directions. Structural engineers, however, have proposed that the constantly changing wall orientation may provide an additional mechanical benefit. Long, uninterrupted walls tend to transmit seismic forces continuously along their entire length. whereas repeated changes in direction interrupt stress paths and distribute loads into multiple segments. Although this hypothesis remains under investigation, finite element simulations indicate that irregular geometry can reduce localized concentrations of force, raising the possibility that defensive planning and structural resilience were achieved simultaneously through the same architectural design. Even the connections hidden within the walls continue to generate debate. Detailed surveys have revealed that many stones are not merely pressed together across flat surfaces. Instead, some incorporate subtle projections, recesses, and three-dimensional interlocking features that prevent individual blocks from sliding independently. Removing a single stone would often require moving several neighboring blocks first, because the entire assembly behaves as a mechanically integrated system rather than a stack of separate components. Since much of this internal geometry remains concealed beneath adjoining stones, researchers cannot fully reconstruct the complete locking mechanism without dismantling the monument itself, something that preservation efforts rightly prohibit. Transporting the stones from nearby quarries remains one of the least understood stages of construction. Most of the andesite originated several kilometers from the fortress, requiring enormous blocks to be moved across uneven mountain terrain at nearly 3,700 meters above sea level. The Inca possessed no iron tools, no wheeled vehicles capable of hauling such loads, and no large draft animals comparable to horses or oxen. Experimental studies suggest that hundreds of workers using braided fiber ropes, wooden rollers or sledges, earthen ramps, and carefully coordinated labor could theoretically move extremely heavy stones. Yet no experiment has successfully reproduced the transportation and final placement of the largest blocks under authentic Andean conditions, leaving significant uncertainty regarding the exact construction sequence. Perhaps the strongest evidence of Sacsayhuaman's engineering achievement lies not in speculation, but in history itself. During the major earthquakes that struck colonial Cusco, countless Spanish buildings constructed with stone and mortar cracked or collapsed entirely, while many of the Inca walls at Sacsayhuaman remained standing with only minimal displacement. The contrast became so striking that Spanish builders eventually reused Inca foundations as the structural bases for churches and government buildings, having learned through experience that Inca construction techniques often performed better than their own. Amiternum was rediscovered beneath fields near San Vittorino, about 9 kilometers north of L'Aquila, in central Italy's upper Aterno Valley. Excavation of its Roman theatre began in 1878 under Angelo Leosini, while the amphitheatre, whose walls had remained partly visible for centuries, was fully exposed only at the end of the 1960s. Between 2006 and 2013, archaeologists from the University of Cologne used magnetometry, aerial and satellite imagery, total station measurement, laser scanning, and 25 targeted excavation trenches to reveal that the monuments were only fragments of a far larger city still buried below the plain. The discoveries transformed Amiternum from a collection of isolated ruins into a difficult engineering question. The settlement began as a Sabine center associated with the nearby hill of San Vittorino, but after Roman expansion into the region, around the beginning of the 3rd century BC, its main functions shifted toward the low ground beside the Aterno River and the Via Casilia. Building an administrative center here required more than placing monuments beside a road. Roman surveyors had to organize streets, public buildings, water infrastructure and properties across a valley floor divided by a river, while connecting them with older routes leading into the surrounding Apennines. Geophysical maps now reveal a forum, basilica, baths, temples, commercial buildings, an aqueduct and residential complexes arranged around this network. Yet the original surveying sequence remains unknown because no construction plans or engineering records have survived. The greatest puzzle is the imbalance between the city's monumental infrastructure and its surprisingly small residential population. Amiternum possessed the public architecture expected of an important Roman centre, but geophysical investigation found comparatively little densely occupied housing. The most extraordinary residence was a building of approximately 6,000 square meters between the theatre and forum, containing an atrium, 2 peristyles, and a large garden, making it the largest known late Republican or early imperial house of its type. Around it stood administrative, commercial, and religious structures serving a population that appears to have lived largely in villas, farms, and roadside settlements dispersed across the valley, some within a radius of about 5 kilometers. Amiternum may therefore have operated less like a conventional city and more like an engineered service center for a wide pastoral territory, but researchers still debate how traffic, markets, livestock movement, and public gatherings were coordinated through a town with so little permanent housing. This unusual urban system depended on the Via Cassilia, which crossed Amiternum and linked its principal districts. Secondary streets, the aqueduct, and major public spaces developed around the road, while the Forum and Basilica occupied the administrative sector north of the river. Other monumental buildings extended across the southern side, forcing engineers to integrate separate zones into a single functioning landscape. The surviving evidence shows the completed arrangement but not the method by which Roman surveyors transferred alignments over long distances or preserved them through several centuries of rebuilding. Instruments such as the groma, measuring rods, water levels, and sighting devices could produce accurate layouts, yet practical knowledge depended heavily on trained specialists whose procedures were rarely written down in enough detail to reconstruct an entire project. The theatre provides the clearest surviving example of that lost process. Constructed between approximately 50 and 25 BC, it could accommodate about 3,000 spectators and used the natural slope near San Vittorino to support part of its semicircular seating. Its builders still had to calculate the curvature of the cavea, access routes, sight lines, and the relationship between the audience and stage. Near the end of the 1st century BC, they altered the building by adding an architectural stage backdrop and a mechanism for raising and lowering a curtain. Unlike a modern curtain descending from above, Roman theatre curtains were probably operated from a narrow trench in front of the stage by a coordinated system of posts, ropes, and counterweights. At Amiternum, only the structural setting survives, leaving the exact arrangement of timber, metal fittings, and lifting equipment uncertain. The theatre was not a fixed design completed in a single campaign. Brick columns and another staircase were added near the end of the 1st century AD, while decorative limestone, statues, and water features transformed the surrounding area. A large pool once stood in front of the building, and fragments of sculpture and architectural decoration were later recovered from it. Integrating a pool beside a heavily used performance complex would have required controlled water delivery, drainage, and foundations able to limit settlement, but much of this infrastructure remains buried. The theatre continued hosting performances until the middle of the 4th century AD, meaning that its seating, stage machinery, and circulation routes remained repairable for nearly 400 years. A short distance away, the amphitheatre presented a different structural challenge. Built during the second half of the 1st century AD, it held approximately 5,000 spectators and was formed as an ellipse supported by 3 levels of brick arches and vaults. Instead of relying mainly on a hillside, its seating rose above an artificial load-bearing framework. Repeating arches distributed the weight downward, while vaulted corridors carried spectators through the structure, allowing thousands of people to enter circulate and leave without crossing the arena. The northern facade required restoration during the first half of the 2nd century, showing that Roman builders monitored structural weakness and repaired major components rather than abandoning the monument. Yet its construction history is becoming more complicated. Excavations in 2025 exposed foundation walls belonging both to the amphitheatre and to the neighbouring building traditionally called the Peristyle House. Archaeologists confirmed that this building existed before the amphitheatre, meaning the entertainment complex was inserted into an already occupied urban area rather than erected on empty land. Engineers therefore had to adapt new foundations, circulation routes, and external spaces to pre-existing architecture. Until larger areas are excavated, it remains impossible to determine how much of the earlier complex was demolished, incorporated, or deliberately preserved beneath the later monument. The function of the peristyle building is itself unresolved. Its scale and position beside the amphitheatre suggest that it may have been a marketplace, the headquarters of a professional association, or a building connected with gladiators and the organization of spectacles. Recent excavation revealed rooms with black and white mosaics and painted plaster, evidence that it was more elaborate than a simple service yard. If it supported the amphitheatre, it may have contained administrative rooms, storage, training areas, or spaces for commercial activity, but no inscription has yet identified its purpose. The mystery is therefore not only architectural, it concerns the operating system behind Roman mass entertainment, including the management of performers, animals, equipment, food, security, and several thousand spectators. Amiternum also stood in one of Italy's most seismically active regions. Archaeological evidence indicates that a major earthquake in the 4th century AD probably damaged the city and contributed to its decline. This does not prove that Roman builders possessed an unknown earthquake-resistant technology, because several buildings were damaged, altered, or abandoned. What the surviving structures do reveal is a practical tradition of thick masonry, repeated arches, vaults, slope-supported seating, and repairable components that distributed loads effectively without modern reinforcement. Determining whether these choices reflected deliberate seismic experience or simply normal Roman construction remains difficult because the same methods were used across regions with very different geological conditions. After the monuments lost their original purposes, their engineering continued to shape later occupation. Houses and a cemetery dating from the 5th to 9th centuries were built over the theatre, while a stone-bordered road crossed its seating area during the 15th century. Elsewhere, a former elite house was reused during the 5th and 6th centuries for metalworking, with imported amphorae and African fine wares, showing that economic connections survived after monumental urban life had weakened. These transformations demonstrate that Roman buildings were not simply abandoned ruins. Their walls, floors, water routes, and open spaces became frameworks for entirely new activities. In northeastern Bulgaria, beneath the modern city of Silistra near the Danube, lies ancient Durostorum, a Roman frontier fortress whose greatest mystery is not its walls, but a painted tomb that has survived almost perfectly for more than 16 centuries. Silistra is the site of the Roman city of Durostorum. Established as a military fortress on the lower Danube during the late 1st century AD and becoming the permanent base of Legio XI, Claudia. Archaeological excavations carried out throughout the 20th century revealed extensive Roman defenses, streets, water infrastructure, and, in 1942, an extraordinary underground mausoleum dating to the middle of the 4th century AD. Today, Silistra Roman Tomb. is recognized as one of the finest preserved examples of late Roman funerary painting in southeastern Europe, and has been included on Bulgaria's UNESCO tentative list because of its exceptional artistic and historical significance. Among everything uncovered at Durostorum, the tomb remains the greatest technological puzzle because nearly every surface inside the burial chamber is covered with remarkably preserved frescoes despite spending more than 1,600 years underground. Archaeologists have identified portraits of servants, floral garlands, peacocks, hunting scenes, geometric ornaments and architectural motifs painted across the vaulted chamber with an artistic quality rarely preserved elsewhere in the Roman world. Scientific analyses show that many of the pigments were derived from naturally occurring minerals, including iron oxides for red and yellow tones, carbon black for dark outlines, and calcium-based white pigments applied over carefully prepared lime plaster. These materials were common throughout the Roman Empire, yet the exceptional state of preservation at Silistra cannot be explained simply by the choice of pigments. The paintings retain unusually vivid color transitions, delicate brushwork, and sharply defined outlines that normally deteriorate after centuries of exposure to moisture, salt migration, and biological activity. Researchers therefore believe that the survival of the murals resulted from a combination of sophisticated plaster preparation, stable underground microclimatic conditions, and the tomb's fortunate sealing shortly after antiquity. But the precise contribution of each factor remains impossible to quantify because the original construction process was never recorded. The engineering of the plaster itself presents another unresolved question. Roman wall paintings were normally executed using multiple layers of lime plaster applied with carefully graded aggregates before pigments were painted onto the fresh surface using the fresco technique. Microscopic examination of the Silistra murals has confirmed this layered structure, yet the exact composition differs subtly from many contemporary sites. Some samples reveal exceptionally dense crystalline bonding between the lime binder and mineral aggregates, producing a surface that resisted flaking for more than 16 centuries despite seasonal temperature fluctuations above ground. Modern conservation scientists understand the underlying chemistry of lime carbonation, in which calcium hydroxide reacts with atmospheric carbon dioxide to form stable calcium carbonate, but they cannot fully reconstruct the original mixing ratios, curing conditions, or craftsmanship that produced such long-term durability. Small variations in aggregate size, moisture content, or curing time can dramatically influence the final mechanical strength, and those practical details disappeared with the craftsmen themselves. The tomb also raises questions about Roman environmental engineering. Unlike monumental temples exposed to wind and rain, this chamber remained buried beneath layers of soil that created an unusually stable internal environment. Measurements collected during modern conservation projects show that underground temperature and humidity fluctuate far less than conditions outside, greatly slowing chemical weathering and biological growth. Even so, countless Roman tombs with similar underground settings have lost most of their paintings through salt crystallization, groundwater infiltration, or microbial damage. Silistra somehow escaped much of this deterioration. Archaeologists suspect that the builders selected a location with favorable geological drainage while designing masonry capable of limiting water penetration. Yet no surviving Roman text explains how local engineers evaluated underground moisture or predicted the long-term behavior of the surrounding sediments. The result is a monument whose preservation appears almost accidental, although accumulating evidence suggests that careful engineering decisions played an important role. As remarkable as the tomb itself is, it existed within one of Rome's most strategically important frontier cities. Durostorum occupied a commanding position along the lower Danube, one of the empire's principal defensive frontiers stretching for hundreds of kilometers. The fortress protected military crossings while controlling trade and communication between the Balkans and territories north of the river. Maintaining a permanent legion required enormous logistical organization. A Roman legion typically numbered around 5,000 to 6,000 soldiers, accompanied by civilians, craftsmen, merchants, and support personnel, who transformed the fortress into a thriving urban center. Supplying this population demanded reliable water, drainage, storage facilities, and transportation infrastructure capable of operating throughout the year. That necessity makes another engineering question particularly interesting. The Danube is Europe's second longest river, extending approximately 2,850 kilometers from Germany to the Black Sea, yet relying directly on river water presented obvious challenges. Seasonal flooding, suspended sediment, and contamination made untreated river water unsuitable for continuous urban consumption. Excavations at Durostorum have revealed wells, cisterns, drainage channels, and water management structures, demonstrating that Roman engineers invested heavily in hydraulic infrastructure. What remains uncertain is the complete configuration of the city's water supply network, because much of ancient Durostorum lies beneath the modern city of Silistra. Geophysical surveys suggest additional buried structures, but large-scale excavation is impossible in densely occupied urban districts, leaving substantial portions of the hydraulic system hidden from investigation. The fortress walls provide another example of Roman engineering that is understood in principle but not in every practical detail. Built on terraces overlooking the Danube, the defenses endured repeated military crises involving Goths, Huns, Avars, Slavs, and later Byzantine reconstruction. Archaeological evidence shows multiple rebuilding phases rather than a single uninterrupted structure, yet portions of the Roman masonry continued serving successive civilizations for centuries. The durability largely resulted from carefully cut limestone blocks combined with lime mortar containing crushed ceramic fragments, a material capable of producing hydraulic reactions that improved resistance to moisture. Laboratory analysis confirms the presence of these ceramic additives, similar to other Roman mortars across the empire, but local variations in raw materials and construction techniques make it difficult to reproduce exactly the mechanical performance observed in surviving structures. Even modern conservation projects continue studying why certain Roman mortars maintain structural integrity after nearly 2,000 years, while many later constructions deteriorate much more rapidly. The layout of Durostorum reflects the remarkable precision of Roman military planning. Excavated streets follow the familiar, orthogonal grid characteristic of legionary fortresses, organizing barracks, workshops, administrative buildings, and storage facilities with impressive regularity. Roman surveyors achieved this alignment using instruments such as the groma for establishing right angles and the chorobates for measuring level gradients during hydraulic construction. Ancient authors, including Vitruvius, described these instruments, yet written descriptions alone cannot reveal the practical expertise required to transfer geometric plans onto uneven terrain with consistent accuracy across an entire fortress. Archaeological remains preserve the finished result, but almost none of the temporary surveying markers, wooden measuring devices, or construction procedures that transformed theoretical geometry into functioning infrastructure. Masada rises above the Dead Sea in southeastern Israel, crowning an isolated rock plateau where an entire fortress has remained standing for more than 2,000 years, despite occupying cliffs that engineering suggests should have become progressively unstable long ago. Although the dramatic Roman siege made Masada famous for centuries, Its true architectural complexity only became clear after systematic excavations led by Yigael Yadin between 1963 and 1965, followed by decades of geological mapping, structural surveys, aerial photography, laser scanning, and conservation studies that revealed one of the most sophisticated mountain fortresses ever built during the reign of Herod the Great, between approximately 37 and 31 BCE. The greatest mystery is not the fortress itself, but the ground beneath it. Masada occupies the summit of an isolated mesa overlooking the Dead Sea, rising roughly 450 meters above the surrounding landscape, while the plateau extends for nearly 600 meters in length and about 300 meters in width. Much of the northern palace and several defensive walls stand astonishingly close to sheer cliffs where gravity, erosion, and repeated seismic activity should have gradually weakened the underlying rock. Geological surveys show that the mesa consists primarily of dolomite and limestone, resting above softer marl layers, formations that commonly develop fractures as weathering progresses. Yet after more than 20 centuries, much of the original foundation remains remarkably stable. Modern engineers can explain why the plateau is relatively resistant, but they still cannot fully reconstruct how Herod's builders determined which cliff edges could safely support thousands of tons of masonry without triggering large-scale slope failure. No surviving Roman or Judean documents describe the surveying methods, foundation preparation, or rock testing that must have preceded construction on terrain that even today would require detailed geotechnical analysis. That unanswered question becomes even more remarkable when the northern palace is examined in detail. Rather than placing a royal residence safely in the center of the plateau, Herod ordered an elaborate three-level palace to be constructed directly against the northern cliff. 3 terraces descend the rock face one beneath another, connected by stairways carved into the mountain itself. The lowest levels project toward open space, with massive retaining walls supporting elegant halls and semicircular balconies overlooking the Dead Sea. The builders achieved this without reinforced concrete, steel anchors, or deep-drilled foundations. Instead, carefully shaped limestone blocks, lime mortar, retaining walls, and precisely distributed loads appear to have transferred enormous weight into selected portions of the cliff. Although restoration has stabilized damaged sections, the surviving original masonry demonstrates an understanding of load distribution that continues to impress structural engineers. Exactly how ancient surveyors calculated these safe-bearing zones remains uncertain, because none of the construction records have survived. The surrounding landscape makes that achievement even more difficult to explain. Masada lies within the influence of the Dead Sea Transform, one of the Middle East's major active fault systems extending for more than 1,000 kilometers. Historical sources and geological evidence indicate that destructive earthquakes struck the region in 31 BCE, 363 CE, 749 CE, and during several later events capable of damaging settlements throughout the Jordan Rift Valley. Despite repeated seismic shaking over 2 millennia, substantial sections of Masada's fortifications remain standing. Archaeological investigations suggest that many defensive walls were constructed using a casemate design consisting of 2 parallel stone walls filled with smaller stones, earth, and interior chambers. Modern structural analysis indicates that this arrangement distributes stress more effectively than a single solid wall, while reducing overall weight, allowing limited movement during seismic events without catastrophic collapse. Whether Herod's engineers intentionally designed these walls for earthquake resistance cannot be proven, but their long-term survival demonstrates a remarkable practical understanding of structural behavior. Even if the buildings could survive earthquakes, another engineering challenge seems almost impossible. Masada occupies one of the driest regions in the Levant, where annual rainfall averages only around 50 millimeters, almost all arriving during short winter storms. Permanent springs do not exist on the summit, yet the fortress supported hundreds of residents and could shelter far larger populations during military emergencies. To solve this problem, Herod's engineers created one of the most advanced ancient water systems ever constructed in a desert environment. Channels cut into surrounding slopes intercepted seasonal flash floods flowing through nearby wadis before directing the water into a chain of enormous cisterns carved into the mountainside below the fortress. Archaeological estimates suggest the complete storage system held approximately 40,000 to 50,000 cubic meters of water, enough to sustain a prolonged occupation. The entire network functioned entirely through gravity, requiring no pumps or mechanical lifting devices. The precise gradients of the channels remain remarkably accurate despite the rugged terrain, demonstrating careful hydraulic planning that continues to attract engineering study. Equally impressive is the durability of the reservoirs themselves. Water storage structures exposed to intense desert heat, dissolved salts, and repeated wetting and drying normally deteriorate rapidly. Yet many of Masada's cisterns preserve their original waterproof lining. Laboratory analysis has identified sophisticated lime plaster, incorporating carefully graded aggregates and crushed ceramic fragments that improved both strength and water resistance. Similar hydraulic plasters are known elsewhere in the ancient Mediterranean, but the exact production methods, firing temperatures, and mixing proportions that produced such long-lasting performance remain only partially understood because ancient technical manuals describing the process have not survived. As the investigation expands across the plateau, evidence repeatedly suggests that nearly every major structure was carefully adapted to the natural topography rather than forcing the mountain into an artificial shape. Drainage channels guided intense seasonal rainfall away from foundations before destructive erosion could develop. Retaining walls stabilized vulnerable slopes, and terraces followed the strongest portions of the underlying bedrock. These solutions appear deceptively simple, yet together they created a fortress capable of enduring conditions that routinely destroy exposed mountain architecture. Modern geological surveys continue to identify erosion scars surrounding the mesa, while the principal occupation areas remain comparatively stable, suggesting the builders possessed an exceptionally accurate practical understanding of local geology without the benefit of modern instruments. The logistics behind the project remain another unresolved puzzle. During Herod's reign, enormous quantities of dressed limestone, timber, plaster, decorative stone, food supplies, and construction equipment had to reach the isolated summit in an environment where summer temperatures frequently exceed 40 degrees Celsius. Archaeologists have identified ancient access routes and construction phases, but no surviving documents explain how thousands of tons of material were transported, organized, and assembled with such precision on an elevated plateau surrounded by steep cliffs. Every completed wall, therefore, represents not only architectural skill, but also an extraordinary level of planning that has largely disappeared from the historical record.
Lubicza Królewska is an archaeological site in southeastern Poland, near the modern border with Ukraine. Beneath its quiet farmland lies evidence of communities that developed surprisingly advanced technologies thousands of years before writing reached this part of Europe. The site came to wider archaeological attention through systematic excavations and surveys that revealed settlements associated with Neolithic and early Bronze Age cultures, including funnel beaker and corded ware communities. What researchers uncovered was not a lost city or monumental temple. Instead, they found something that may be even more mysterious. evidence of technological knowledge that should have been difficult for small farming societies to develop, preserve, and transmit over centuries. The first mystery involves the construction of large timber buildings. Archaeologists identified post holes indicating the existence of longhouses stretching more than 30 meters in length. Such structures required hundreds of trees and thousands of hours of labor. Experimental archaeology projects conducted in Central Europe have shown that felling a single mature oak using polished stone axes can require hours of continuous work. Building an entire settlement would therefore have demanded a level of organization that seems surprisingly sophisticated for communities without writing, centralized governments, or metal tools. Researchers still debate how these projects were coordinated. Did village leaders organize labor through social authority? Were construction techniques shared between distant communities? Or did specialized builders travel across regions carrying technical knowledge with them? The archaeological evidence remains incomplete. The second mystery concerns settlement planning. Surveys reveal that many structures appear to follow consistent orientations. This may seem insignificant today, but maintaining directional accuracy across multiple generations requires some method of measurement. Without compasses or formal surveying instruments, the inhabitants may have relied on solar observations, landscape markers, or inherited construction traditions. Similar questions have emerged at sites such as Çatalhöyük in Turkey and Skara Brae in Scotland, where surprisingly organized layouts challenge assumptions about early farming societies. The third mystery is perhaps the most fascinating of all: the underground storage pits and food preservation systems discovered throughout the settlement. At first glance, these pits appear simple. They are merely excavated holes in the ground. Yet, closer examination suggests that they may represent one of the most important technological achievements of prehistoric Europe. For early agricultural communities, food storage was a matter of survival. Harvests occurred only once per year, but people needed food every day. A failed storage system could mean famine, disease, and social collapse during winter. Many of the pits found at Libica Królewska display recurring shapes and dimensions, suggesting that their builders followed established design principles. Archaeologists have long noted that underground storage pits can create remarkably stable environmental conditions. Soil acts as a natural insulator, reducing temperature fluctuations compared with surface structures. Modern studies of underground grain storage have demonstrated that temperatures several feet below ground remain significantly more stable throughout the year. In parts of Europe, subsurface temperatures often fluctuate only a few degrees despite large seasonal changes above ground. Such stability slows spoilage and helps protect stored crops. The mystery is how Neolithic communities discovered these principles. Nobody recorded the experiments. No written manuals survive. Yet the evidence suggests that people understood how depth, shape, soil composition, drainage, and ventilation influenced preservation. Some pits appear deliberately positioned in locations with favorable drainage conditions. Others may have incorporated organic linings or coverings that improved storage performance. Researchers continue to investigate exactly how these systems functioned. The challenge becomes even more intriguing when compared with other ancient civilizations. In ancient Egypt, grain was stored in massive state-controlled granaries. In Mesopotamia, written records documented agricultural inventories. At Libica Królewska, however, similar storage goals were achieved without bureaucracies, writing systems, or monumental architecture. The technology itself was invisible. Unlike pyramids or temples, underground storage systems leave few traces behind, yet they may have been equally important to survival. A village capable of preserving grain through harsh winters could support larger populations, withstand poor harvests, and invest labor into construction, trade, and craft production. Some researchers argue that food storage technologies may have played a role in the rise of social complexity across prehistoric Europe. Communities capable of producing and preserving surplus resources gained advantages over neighboring groups. If this interpretation is correct, the humble storage pits at Lubica Królewska may represent an early form of agricultural engineering that helped transform European society. Even today, archaeologists cannot fully reconstruct the knowledge behind these systems. We can measure the pits, we can analyze pollen and plant remains, we can estimate storage capacity, but we still do not know exactly how generations of farmers refined these designs without written science. The fourth mystery involves long-distance exchange networks. Stone tools recovered at the site reveal that some raw materials originated far from the settlement itself. High-quality flint often traveled hundreds of kilometers across Central Europe. Such movement required routes, partnerships, and communication between distant communities. This creates a logistical puzzle. Transporting valuable stone across large distances without roads, carts, or organized states demanded considerable planning. Similar exchange networks have been documented throughout Neolithic Europe, but many details remain unknown. How did traders navigate? How was trust maintained between communities that may never have met before? What mechanisms protected valuable resources during transport? Archaeologists continue searching for answers. The fifth mystery concerns the remarkable precision of flint craftsmanship. Many recovered blades demonstrate extraordinary skill. Producing long, thin cutting edges from brittle stone requires precise control of force and angle. Modern experimental knappers often spend years mastering techniques that prehistoric artisans performed routinely. The existence of such expertise suggests specialized training, yet there is no evidence of schools, manuals, or written instruction. Knowledge must have been transmitted directly from person to person across generations. How this technical education functioned remains uncertain.
Trajan's bridge stood across the Danube between present-day Drobeta Târnu Severin in Romania and Kladovo in Serbia. Yet the first clues to how extraordinary it truly was emerged not from the surviving ruins above water, but from centuries of archaeological investigation beneath the river itself. Medieval travelers still described isolated stone piers rising from the current, while systematic excavations during the 19th and 20th centuries, followed by underwater archaeology, bathymetric mapping, aerial photography, LiDAR surveys, and structural analysis, gradually revealed that these remains belonged to what was once the longest bridge ever constructed in the ancient world. Built between AD 103 and 105 under Emperor Trajan, and designed by the renowned engineer Apollodorus of Damascus, the bridge stretched approximately 1,135 meters across one of Europe's largest rivers, supported by 20 massive masonry piers that carried a timber superstructure roughly 15 meters wide. Although only fragments survive today, the archaeological evidence immediately raises a question that becomes more difficult the deeper researchers investigate. How did Roman engineers build foundations capable of resisting the Danube for nearly 2,000 years, when many modern bridges require extensive reinforcement after only decades? The mystery begins with the river itself. Even today, the Danube remains one of Europe's most powerful waterways, carrying enormous seasonal variations in discharge that can exceed 10,000 cubic meters of water per second during major floods, while transporting vast quantities of sediment, drifting ice, and floating debris capable of damaging modern bridge piers. The section chosen for Trajan's bridge was nearly 1 kilometer wide, with an unstable riverbed composed of gravel, sand, and alluvial deposits constantly reshaped by changing currents. Modern hydraulic engineering recognizes scour around bridge foundations as one of the leading causes of bridge failure, because fast-moving water removes supporting sediments until heavy piers begin to settle or collapse. Yet underwater investigations have shown that several of Trajan's massive foundations remained remarkably stable long after the timber deck disappeared, suggesting that Roman surveyors possessed a far more sophisticated understanding of river hydraulics than surviving written sources can explain. That question becomes even more intriguing when attention turns to the construction process itself. Most historians believe Apollodorus relied on enormous timber cofferdams to isolate sections of the river so that foundations could be built in dry conditions. But no contemporary engineering manual describes exactly how these structures functioned on the Danube. Vitruvius discussed construction techniques for marine works more than a century earlier, yet he never described a project remotely comparable in scale. Archaeological remains indicate that each masonry pier measured roughly 38 meters long, about 19 meters wide, and nearly 44 meters high from foundation to deck level. Dimensions that would have required excavation far below the river surface, while resisting tremendous hydrostatic pressure. Engineers today can model possible cofferdam arrangements using computational fluid dynamics, but none fully explain how Roman builders prevented leakage, stabilized temporary walls against powerful currents, removed groundwater, or maintained safe working conditions over months of construction without modern pumps or steel sheet piling. The absence of detailed technical documentation has left one of antiquity's greatest engineering operations largely hidden behind educated reconstruction rather than direct evidence. As researchers examined the surviving masonry more closely, another puzzle emerged from the remarkable durability of the bridge's foundations. Unlike freestanding monuments exposed mainly to gravity, bridge piers must endure constant horizontal loading produced by water pressure, debris impacts, thermal expansion, and seasonal ice. Geological surveys suggest that the Danube has altered its channels repeatedly since Roman times, yet several foundations continued resisting erosion despite centuries of hydraulic attack. This resilience implies careful selection of foundation depth and placement before construction even began. Without sonar, drilling rigs, or modern geotechnical equipment, Roman engineers somehow identified locations capable of supporting thousands of tons of masonry while minimizing future scour. How they measured subsurface conditions beneath a fast-flowing river remains uncertain because no Roman text records procedures for underwater geological investigation on this scale. Material science has added another layer to the mystery. Roman concrete has become famous after laboratory studies revealed that volcanic ash mixed with lime produces durable calcium-aluminum silicate hydrates and minerals such as aluminous tobermorite, compounds capable of strengthening concrete through long-term interaction with water. Similar mechanisms have been identified in Roman harbor structures that have survived marine environments for over 2 millennia. Whether identical hydraulic concrete mixtures were employed extensively within Trajan's bridge foundations remains debated, because the Danube lies hundreds of kilometers from the principal volcanic ash deposits around the Bay of Naples, traditionally associated with high-quality pozzolana. Some researchers argue that volcanic materials were transported over extraordinary distances through the Roman logistical network, while others propose that local mineral sources, or alternative aggregate compositions, achieved comparable performance. The exact formulation used beneath the river has never been conclusively established, leaving unanswered questions about how the bridge acquired such exceptional longevity. These uncertainties become even greater when considering the logistics required to assemble the structure. Estimates suggest that constructing 20 enormous piers demanded tens of thousands of dressed stone blocks, immense quantities of mortar, timber, iron clamps, and specialized lifting equipment, all delivered to an active military frontier during Trajan's Dacian campaigns. Reliefs on Trajan's column depict cranes, ships, and construction activity, but they provide only symbolic snapshots rather than detailed engineering drawings. No surviving blueprint explains how stones weighing several tons were positioned with sufficient precision inside confined cofferdams, while currents continuously pressed against temporary retaining walls. Experimental archaeologists have demonstrated that Roman treadwheel cranes could lift impressive loads, yet coordinating dozens of heavy lifts simultaneously across a river nearly 1 kilometer wide would have required planning on a scale unmatched anywhere else in the ancient world. The tension then shifts upward to the timber superstructure, another aspect that challenges conventional expectations. Ancient sources, including Cassius Dio, indicate that wooden arches or beams connected the masonry piers, creating a crossing capable of supporting the rapid movement of Roman legions into Dacia. Individual spans were approximately 50 meters long, extraordinary distances for timber construction before industrial engineering. Wood naturally expands, contracts, absorbs moisture, and gradually deteriorates under repeated loading, especially in climates with freezing winters and hot summers. Roman carpenters undoubtedly possessed remarkable woodworking skills, yet the precise structural system allowing repeated military traffic across such long spans has disappeared completely because the timber was dismantled, probably during the reign of Hadrian, after the Dacian Wars had ended. As a result, historians understand the stone supports far better than the bridge deck they once carried.
The discovery of Angkor Thom lies near modern Siem Reap, Cambodia, at the heart of the ancient Khmer Empire. Although European explorers documented the ruins during the 19th century, the true scale of the city remained unknown for more than a century. Everything changed in the early 21st century when archaeologists began using airborne LiDAR technology. By firing millions of laser pulses through the jungle canopy, researchers revealed an enormous urban landscape hidden beneath the forest. What appeared to be a collection of temples turned out to be part of one of the largest pre-industrial cities ever built. Surveys conducted by the Greater Angkor Project revealed an urban complex covering more than 1,000 square kilometers, transforming Angkor from a famous archaeological site into one of the most important engineering mysteries on Earth. The first mystery is the hydraulic system itself. Angkor Thom was not simply a walled city, but the center of an immense network of reservoirs, canals, embankments, spillways, and artificial waterways designed to control seasonal monsoon floods. The scale of this system is astonishing. The nearby West Barre Reservoir measures approximately 8 kilometers long and more than 2 kilometers wide, containing an estimated 50 million cubic meters of water. To put that into perspective, the reservoir holds enough water to fill roughly 20 Olympic swimming pools. Across the Angkor region, multiple reservoirs and canals work together to store, transport, and redistribute water throughout the year. Modern hydrologists studying the system have discovered evidence of remarkable sophistication, showing that water could be redirected through interconnected channels depending on seasonal conditions. During heavy monsoon rains, excess water could be diverted away from critical infrastructure, while during dry periods, stored water could support agriculture. Yet the greatest question remains unanswered. How did Khmer engineers design and maintain such a vast hydraulic network without modern surveying, equipment, advanced mathematics, or industrial construction technology? Even today, managing water across 1,000 square kilometer landscape requires complex engineering models, yet the Khmer accomplished it more than 800 years ago. The second mystery involves precision city planning. Angkor Thom was established during the reign of King Jayavarman VII in the late 12th century and forms an enormous square approximately 3 kilometers on each side. Massive walls surround the city, while a moat nearly 100 meters wide encircles the entire perimeter. The gates align closely with the cardinal directions. Such precision might appear ordinary on a modern map, but constructing a nearly perfect geometric city within a tropical environment presented extraordinary challenges. Surveyors today use GPS receivers capable of centimetre-level accuracy, yet medieval Khmer engineers possessed no such tools. Nevertheless, they created a city whose overall alignment rivals that of many famous ancient capitals. Similar achievements are often discussed in relation to places such as the Egyptian pyramids or Roman military camps, and Angkor Thom belongs in the same conversation. Archaeologists still debate the exact techniques used to establish these alignments across such a large area. The third mystery concerns the construction of Bayon Temple, the spiritual centre of Angkor Thom. Bayon contains more than 50 towers decorated with over 200 enormous stone faces. Each face rises several meters high and was carved with extraordinary symmetry. Some scholars believe the faces represent Avalokiteshvara, the Buddhist bodhisattva of compassion, while others suggest they may portray Jayavarman VII himself. The engineering challenge is extraordinary because many of these faces sit dozens of meters above ground level, yet their proportions remain remarkably consistent, despite being positioned on complex tower structures. Researchers continue to debate whether the faces were carved before the blocks were lifted into position or after construction was completed. If they were carved on the ground, engineers had to achieve near-perfect placement during assembly. If they were carved in place, workers would have needed elaborate scaffolding systems and highly precise measuring techniques. No written records survive to explain how this process was carried out. The fourth mystery involves transportation. Most of the sandstone used in Angkor Thom originated from quarries in the Kulin Hills, approximately 30 to 40 kilometers away. Millions of stone blocks were transported across rivers, canals, and difficult terrain, with some blocks weighing several tons. Modern estimates suggest that tens of millions of tons of stone were moved throughout the Angkor region over centuries of construction. Comparisons help illustrate the scale of this achievement. The Great Pyramid of Giza contains roughly 2.3 million stone blocks, yet Angkor's total building program extended across a much larger urban landscape and required the continuous movement of construction materials over long distances. Archaeologists have identified ancient canals linking quarry areas to the city, suggesting that water transport played a major role. However, the complete logistics system remains poorly understood. Questions remain regarding how many workers were involved, how long transportation took, and how massive stones were loaded and unloaded without cranes. The available evidence remains incomplete. The fifth mystery is hidden beneath the ground. Angkor Thom was constructed in a region heavily affected by seasonal flooding and unstable soils. Despite these conditions, many structures have survived for more than 8 centuries. Engineers appear to have understood drainage, soil stabilization, and load distribution at a sophisticated level. Modern geotechnical studies reveal carefully prepared foundations beneath major monuments, while water management features often worked together with structural engineering solutions. In some locations, canals and reservoirs may have helped regulate groundwater levels. This raises an important question. Did Khmer engineers possess practical knowledge of soil mechanics centuries before the scientific principles were formally understood? The surviving structures suggest that they may have. The sixth mystery concerns population support. Angkor has often been compared with the largest cities of the medieval world. Some estimates suggest that the Greater Angkor region may have supported between 700,000 and 1 million inhabitants at its peak. If accurate, this would place Angkor among the most populous urban centres on Earth during the 12th and 13th centuries. Supporting such a population required enormous agricultural productivity. Rice cultivation depended on reliable water control, while food distribution required extensive infrastructure. Labour organisation had to coordinate construction, maintenance, transportation, and administration. Yet the Khmer left surprisingly few records explaining how this gigantic urban machine functioned. The physical evidence demonstrates success, but the organisational mechanisms behind that success remain largely invisible. The seventh mystery is the collapse of the system. By the 15th century, Angkor's political importance had declined dramatically. Researchers investigating sediment cores, tree rings, and climate records discovered evidence of severe environmental instability. Southeast Asia experienced prolonged droughts interrupted by episodes of unusually intense rainfall, and these extreme climate events may have placed enormous stress on the hydraulic network. Computer simulations suggest that parts of the water management system became increasingly vulnerable over time. Channels eroded, reservoirs accumulated sediment, and infrastructure required constant maintenance. Some scholars believe Angkor became a victim of its own complexity. As the larger the system grew, the harder it became to manage. Yet, no single explanation fully accounts for the decline. Climate change, political conflict, shifting trade routes, and institutional challenges may all have contributed, and the exact sequence of events remains uncertain.
Buried within the dense forests of Campeche in southern Mexico, Hochob Archaeological Zone remained concealed beneath vegetation for centuries before modern archaeological surveys began documenting the site in the 20th century. The name Hochob roughly translates to place of the ears of corn, yet the city became known for something far more mysterious. Massive stone temples decorated with giant monster-like facades, unlike almost anything else in the Maya world. Unlike famous Maya centers such as Chichen Itza or Tikal, Hochob was built inside remote tropical terrain with no major rivers nearby and no obvious transportation network capable of supporting large-scale construction. Yet archaeologists discovered multi-room palace structures, ceremonial buildings, vaulted corridors, and enormous decorative facades constructed with astonishing precision. The deeper researchers investigated the site, the more Hochob began to look less like a forgotten jungle ruin and more like a technological puzzle left behind by the ancient Maya. The most iconic structures at Hochob are the enormous zoomorphic temple entrances, gigantic stone masks representing supernatural beings whose mouths form the doorway into the temple itself. These facades are composed of hundreds of carefully shaped limestone blocks fitted together with remarkable accuracy. What makes this mysterious is the level of precision achieved without iron tools, steel blades, cranes, or modern measuring equipment. Some joints between stones are so tight that even thin blades struggle to slide between them. Engineers comparing the stonework to later medieval masonry have noted similarities in precision, despite the Maya lacking metal-cutting technology available in Europe centuries later. The limestone used at Hochob is softer than granite, but that alone does not explain the consistency of the cuts. Researchers examining the surfaces discovered evidence of repeated abrasion polishing and controlled shaping techniques that would have required enormous labor coordination. Even more puzzling, many decorative sections appeared geometrically symmetrical across large surfaces, implying the builders possessed advanced planning systems and standardized measurement methods. Several archaeologists have suggested the Maya may have used chord-based geometric grids or proportional systems similar to those later documented in other ancient civilizations. Yet no surviving written technical manuals from the Maya world explain how such massive symbolic facades were designed and assembled so accurately in dense jungle conditions. One of the strangest engineering mysteries at Hochob involves its surviving stucco surfaces. Tropical environments are among the worst possible places for exposed limestone architecture. High humidity, seasonal rainfall, heat, biological growth, and expanding tree roots rapidly destroy exposed structures. In many tropical regions, unprotected stone can degrade severely within centuries. Yet parts of Hochob's stucco decoration have survived for over 1,000 years. Scientific analysis of Maya lime plaster from sites across the Yucatan Peninsula revealed evidence of sophisticated material processing. To produce lime plaster, the Maya heated limestone to temperatures approaching 800–900 degrees Celsius before mixing it with water and additives. Maintaining such temperatures consistently would have required highly organized fuel systems and advanced control of combustion environments. Researchers studying Maya plasters discovered traces of organic compounds, plant extracts, and mineral particles that may have improved water resistance and structural durability. Some modern materials scientists compare these mixtures to experimental self-healing lime mortars, where microscopic chemical reactions allow small cracks to reseal over time through calcite recrystallization. At Hochob, the survival of detailed carvings despite centuries of tropical storms suggests the builders understood environmental engineering at a surprisingly advanced level. Some walls appear capable of shedding water efficiently due to subtle surface angles invisible at first glance. Others show evidence of layered finishing techniques designed to reduce moisture penetration. The mystery becomes even greater when compared to many later colonial structures in tropical America that deteriorated far more rapidly despite access to metal tools and later construction methods. Modern engineers consider tropical limestone terrain extremely difficult for long-term heavy construction. The porous bedrock absorbs water, fractures easily, and shifts over time. Yet Hochob's buildings remained standing through centuries of storms, erosion, and environmental pressure. Archaeological surveys suggest the Maya may have constructed multi-layered foundations, using compacted rubble, crushed limestone, and drainage materials to distribute weight across unstable ground. This resembles principles used in modern geotechnical engineering. What astonishes researchers is the scale of the achievement. Some structures at Hochob weigh thousands of tons collectively, yet they show surprisingly limited subsidence compared to expectations for tropical terrain. Without reinforced concrete, steel frames, hydraulic excavation equipment, or modern soil analysis, the Maya somehow created stable ceremonial complexes capable of surviving for centuries. Comparisons are often made to other ancient civilizations that mastered difficult terrain, such as the Inca foundations at Machu Picchu or Roman harbor engineering along the Mediterranean. But unlike the Romans, the Maya worked without limpozzolana concrete capable of hardening underwater. Unlike the Inca, Hochob existed in humid jungle conditions that accelerate structural decay dramatically. This raises a disturbing possibility. The Maya may have possessed generations of accumulated empirical engineering knowledge far beyond what survives in the archaeological record. Hochob also contains large corbel-vaulted chambers, a hallmark of Maya architecture. Unlike true arches, corbel vaults are formed by stacking stones progressively inward until they nearly meet at the top. Structurally, this method creates enormous lateral pressure and instability. At Hochob, some vaulted corridors appear unusually wide relative to their supporting walls. Modern structural simulations suggest several chambers approach dangerous load thresholds if constructed purely through basic trial-and-error methods. And yet many of these corridors survive for centuries. This suggests Maya architects deeply understood weight distribution, compression forces, and structural balance even without formal mathematical physics. Some researchers believe Maya builders refined their techniques over generations through repeated experimentation across cities in the Pus and Chens regions. The precision becomes especially mysterious considering the environmental conditions. High humidity weakens mortar, biological growth damages joints, and seasonal thermal expansion stresses stone structures continuously. Even so, parts of Hochob's vaulted architecture remain intact long after many younger historical buildings collapsed elsewhere in the world. Several structures at Hochob appear aligned with solar events, especially equinox and solstice positions. This is not unique among Maya cities.
but the consistency of the orientations has generated debate among archaeologists. The Maya possessed one of the most advanced astronomical traditions in the ancient world. They accurately tracked Venus cycles, solar years, eclipses, and complex calendar systems. However, the precision implied at sites like Hochob raises difficult questions. How did observers in dense jungle terrain achieve such consistent alignments without telescopes or precision optics? Some theories suggest the Maya established long-term observational stations using horizon markers and repeated generational measurements. Others argue they may have used architectural sightlines integrated into ceremonial spaces. Comparisons are often drawn to solar alignments at Stonehenge or the astronomical planning of ancient Egyptian temples near Karnak. Yet Hochob's alignments were achieved in a tropical environment where vegetation growth constantly obstructed long-distance visibility. This makes the consistency even more difficult to explain. Perhaps the greatest mystery surrounding Hochob archaeological zone is logistics. The city was built deep inside tropical jungle with no major rivers nearby, while the Maya did not use large draft animals or practical wheeled transport for massive construction projects. Yet thousands of tons of stone were still quarried, moved, and assembled into enormous structures. Simply transporting multi-ton limestone blocks through hot, humid jungle conditions would have required extremely complex labor coordination. Researchers estimate that major Maya cities demanded millions of labor hours to complete large construction projects. The real mystery is not only how the Maya built Hochob, but how they maintained such a precise logistical system in one of the harshest environments imaginable. Do you think the Maya truly possessed engineering knowledge far beyond what history tells us? Share your thoughts in the comments below.
Located in the Pindus Mountains of Thessaly, central Greece, Meteora appears to suspend entire stone monasteries atop towering sandstone pillars that rise as much as 600 meters above the surrounding valleys. More than 6 centuries after they were built, these massive structures continue to stand where geology, erosion, and repeated earthquakes suggest many of them should have gradually failed. Although local hermits had occupied the rock pinnacles for centuries, the first organized monastery at Meteora was established in the mid-14th century by Athanasios the Meteorite. Later travelers, Ottoman records, and modern archaeological surveys gradually documented the remarkable settlement, while geological studies revealed that the spectacular rock towers themselves formed approximately 25 to 30 million years ago from thick deposits of river gravels and sand that later became cemented into conglomerate rock before erosion sculpted the isolated pillars visible today. That geological history immediately raises an engineering mystery, because conglomerate is not an ideal construction material. Unlike granite or dense limestone, it consists of rounded pebbles and cobbles bound together by natural mineral cement, creating a rock mass whose internal strength can vary significantly from one location to another. Weathering gradually weakens exposed surfaces, water infiltrates natural fractures, and repeated thermal expansion slowly enlarges existing cracks. Modern engineers normally approach such formations cautiously because localized failures are difficult to predict. Yet medieval builders chose not only to occupy these pillars, but to place entire monasteries weighing hundreds of tons directly on their summits. The greatest unanswered question is not how the walls were erected, but why their attachment to the underlying rock has remained so remarkably stable for more than 600 years. Unlike castles founded on broad plateaus or deeply excavated bedrock, many Meteora monasteries appear to emerge directly from irregular rock surfaces with almost no visible transition between natural stone and masonry. Archaeological investigations show that builders carefully carved the summit itself into stepped platforms before laying foundations, allowing walls to follow the natural contours instead of forcing the rock into artificial geometry. This approach reduced concentrated stresses while maximizing contact between masonry and bedrock. Yet the exact methods used to anchor structural loads into highly variable conglomerate remain largely undocumented because virtually no medieval construction records describing the process have survived. The durability of those hidden connections becomes even more remarkable when viewed through the lens of structural geology. Conglomerate contains countless rounded stones embedded within finer sediments, meaning every foundation encounters changing mechanical properties over very short distances. Modern geotechnical engineering would normally require extensive mapping of fractures, discontinuities, and bearing capacity before placing heavy loads on such terrain. 14th century builders possessed none of these scientific tools, yet their choice of foundation locations appears extraordinarily selective. Many monasteries occupy the widest, most stable sections of individual pillars, while avoiding areas where major vertical joints or heavily weathered surfaces are now visible. Whether this resulted from generations of empirical observation or an exceptionally sophisticated understanding of rock behavior remains impossible to determine. Equally mysterious is the apparent absence of significant foundation displacement despite centuries of environmental stress. Greece ranks among Europe's most seismically active regions because the African plate continues moving beneath the Eurasian plate along the Hellenic Arc. Historical records document numerous destructive earthquakes affecting Thessaly over the past several centuries, while instrumental observations confirm that moderate seismic activity remains frequent throughout central Greece. During every earthquake, the towering pillars naturally oscillate, transferring dynamic forces into every wall, arch, timber beam, and foundation stone. Yet structural surveys consistently show that most surviving monasteries have experienced remarkably limited large-scale foundation failure compared with what engineers might expect from buildings of similar age constructed on fractured sedimentary rock. Their resilience becomes easier to appreciate when considering how medieval builders distributed weight across the landscape. Rather than concentrating enormous masses in isolated towers, they generally favored relatively low profiles, thick masonry walls, and timber roof systems capable of absorbing part of the seismic energy through controlled flexibility. Wooden beams hidden inside the structures acted as natural energy dissipators, reducing sudden stress concentrations during ground motion. Even so, these principles explain only part of the puzzle, because the hidden interface between masonry and conglomerate still performs the critical task of transferring thousands of tons of cumulative structural load into pillars continuously reshaped by erosion. That same erosion introduces another unanswered question. The rock towers of Meteora have stood exposed to rain, frost, wind, and seasonal temperature fluctuations for millions of years. Water slowly penetrates joints, dissolves mineral cement, and removes weaker sediments grain by grain. Gravity steadily enlarges fractures, eventually producing rockfalls that remain common throughout similar conglomerate landscapes. Nevertheless, the specific summits supporting the monasteries have retained sufficient integrity to preserve buildings that have remained occupied since the Byzantine period. Geologists attribute much of this longevity to unusually strong silica and calcite cement binding many portions of the conglomerate, but natural cementation alone cannot explain why the occupied summits appear disproportionately resistant compared with neighboring cliffs that have experienced repeated collapse. Construction itself presents another extraordinary logistical mystery. During the 14th and 15th centuries, there were no staircases connecting the valley floor with the monastery summits. Every block of stone, timber beam, roof tile, iron fitting, barrel of water, sack of grain, and bell had to be transported vertically using rope ladders, woven nets, and pulley systems suspended hundreds of meters above the ground. Historical descriptions mention these lifting devices, but provide almost no technical detail regarding anchoring systems, mechanical advantage, rope replacement schedules, or methods for stabilizing swinging loads in strong mountain winds. Considering that even a modest monastery required hundreds of tons of construction material, the absence of comprehensive engineering documentation remains one of Meteora's greatest historical gaps. Water management demonstrates another level of practical sophistication. Flat mountaintops exposed to seasonal rainfall can rapidly accumulate runoff capable of undermining foundations or accelerating rock weathering. Instead of allowing water to collect unpredictably, builders integrated stone gutters, drainage channels, underground cisterns, and carefully graded courtyards into the natural topography. Rainwater was directed away from vulnerable foundation zones while simultaneously being stored for daily use, reducing both erosion and dependence on external water supplies. Many of these hydraulic features continue functioning after several centuries with surprisingly limited modification, illustrating an environmental understanding far beyond what surviving written sources reveal. Located on the volcanic Gergovie Plateau in central France, about 8 kilometers south of modern Clermont-Ferrand, stands one of Europe's most underestimated archaeological mysteries. Long remembered as the place where Vercingetorix defeated Julius Caesar in 52 BCE, the plateau preserves evidence of engineering that still raises difficult questions about Iron Age technology. Gergovie is an Iron Age oppidum identified through archaeological excavations beginning in the 19th century and confirmed by extensive research throughout the 20th and 21st centuries, revealing fortified defenses, domestic quarters, workshops, storage facilities, and occupation layers dating mainly to the late La Tène period. The discoveries transformed Gergovie from a legendary battlefield into one of the best laboratories for studying Celtic engineering. Yet every excavation seems to deepen one particular mystery. Beneath collapsed stone walls, archaeologists repeatedly uncovered hundreds of large iron nails, traces of massive timber beams, and carefully arranged masonry belonging to the defensive system known as Murus Gallicus. Julius Caesar described this structure in Commentari de Bello Gallico, and modern excavations have confirmed that his account was remarkably accurate. The walls combined horizontal oak beams locked together by long forged iron spikes, while stone facings and compacted earth formed the exterior. Unlike ordinary dry stone fortifications, this composite design absorbed impact from battering rams instead of shattering under repeated blows. Experimental archaeology has shown that timber frameworks greatly increase resistance to localized collapse, because the wooden skeleton distributes mechanical stress throughout the structure rather than allowing cracks to spread through brittle stone alone. Even more surprising is the quantity of iron required to build such defenses. Archaeologists estimate that large sections of Murus Gallicus consumed many thousands of forged spikes, each individually manufactured by blacksmiths. Some surviving examples exceed 30 centimeters in length, while Caesar himself emphasized that the beams were fastened with iron at regular intervals. Reconstructing walls extending for kilometers suggests that several tens of tons of wrought iron may have been required for a major oppidum, making Gergovie one of the largest known consumers of iron in Iron Age Gaul. That conclusion immediately creates another puzzle, because iron production during the late La Tène period remained extraordinarily labor-intensive. Producing only 1 kilogram of bloom iron required significant quantities of charcoal, together with carefully selected iron ore, continuous furnace operation, and repeated cycles of hammering to remove slag. Modern archaeometallurgical studies estimate that bloomery furnaces generally converted only a fraction of the ore into usable metal, meaning enormous amounts of wood had to be transformed into charcoal before a single defensive wall could even begin construction. Yet no industrial complex surrounding Gergovie has been discovered that matches the scale implied by its fortifications. Excavations have identified evidence of metalworking, including slag and smithing debris, but nothing capable of explaining where the immense volume of finished iron originated. Some researchers suggest production was distributed among multiple regional workshops connected through extensive trade networks across central Gaul, while others argue that many smelting sites remain undiscovered beneath later settlements or forests. Neither explanation has been conclusively demonstrated, leaving the logistics behind one of Europe's largest prehistoric engineering projects only partially understood. The mystery becomes even greater when transportation is considered. Gergovie occupies a volcanic basalt plateau rising roughly 150 meters above the surrounding plain and covering nearly 70 hectares. Every timber beam, every stone block, and every iron spike had to reach the summit without wheeled machinery, steel cranes, or powered transport. Archaeologists have never identified permanent construction ramps, loading platforms, or hauling installations that would explain how such quantities of material were moved uphill. Wooden sledges, rollers, ropes, and coordinated labor almost certainly played a role because comparable techniques are documented elsewhere in the ancient world, yet no direct archaeological evidence demonstrates exactly how construction was organized at Gergovie. As with many prehistoric monuments, the finished engineering survives, while the infrastructure that created it has almost entirely disappeared. The design of Murus Gallicus itself continues to impress engineers because it represents a sophisticated understanding of structural behavior long before formal theories of mechanics existed. Stone supplied compressive strength, timber provided flexibility, while iron prevented the framework from separating under impact. Modern structural analysis shows that composite materials often outperform rigid systems because they combine different mechanical properties within a single structure. Whether Celtic builders developed this concept independently through generations of practical experimentation or inherited specialized knowledge from earlier traditions remains unknown. Archaeology reveals mature engineering, but almost no evidence documenting how the design evolved into such an effective defensive system. Beyond its walls, the plateau also demonstrates remarkable urban planning. Excavations have revealed organized residential districts, storage buildings, workshops, roadways, and defensive gateways, distributed according to the natural contours of the volcanic landscape, rather than random expansion. Instead of forcing the terrain into a geometric pattern, builders adapted the settlement to slopes, drainage routes, and natural defensive positions. Geophysical surveys, together with aerial photography, have helped reconstruct parts of this layout, indicating that planning occurred before large-scale construction rather than developing gradually without coordination. Such organization challenges the long-standing stereotype that pre-Roman Celtic communities lacked sophisticated urban planning. Water management presents another unresolved question. Permanent rivers do not flow across the summit, yet thousands of inhabitants may have occupied the plateau during periods of military concentration. Archaeologists have identified wells, cisterns, and evidence for rainwater collection, but these installations alone do not fully explain how a large defended settlement could sustain its population during prolonged occupation or siege. Some researchers propose that additional underground water sources remain undiscovered beneath volcanic deposits, while others believe storage capacity has simply not survived excavation. Until further evidence emerges, the complete hydraulic system remains uncertain. The volcanic geology also introduced engineering challenges rarely discussed outside specialist research. Basalt is substantially harder than the limestone commonly used elsewhere in Gaul, requiring stronger tools and greater labor to shape foundations and defensive platforms. Even where builders relied primarily on local stone, they still had to level uneven surfaces, stabilize slopes, and construct walls capable of resisting erosion on exposed volcanic terrain. More than 2,000 years of weathering have erased many traces of quarrying, preventing archaeologists from reconstructing the exact sequence of construction techniques employed across the plateau. Historical records add another layer to the mystery. Caesar's account of the Battle of Gergovia is one of the main sources, though he focused more on the fighting than the engineering. Wat Ek Phnom rises from the flat floodplains of northwestern Cambodia, like the remains of a civilization that understood engineering far beyond what historians once believed possible. Archaeologists first documented the temple during French colonial surveys in the late 19th century, but its true complexity only became clear after structural and geological studies revealed something strange. This massive stone monument had survived nearly 1,000 years on unstable tropical soil that should have caused catastrophic collapse centuries ago. Built during the 11th century under the Khmer Empire, Wat Ek Phnom is often overshadowed by Angkor Wat, yet many researchers now believe it may preserve clues about forgotten construction techniques, material science, and environmental engineering that remain only partially understood today. The first mystery begins beneath the temple itself. Battambang sits in a region heavily affected by seasonal flooding, groundwater movement, and soft alluvial sediments. Modern engineers know that constructing multi-thousand-ton stone structures on such terrain is extremely dangerous without deep foundations or reinforced stabilization systems. Yet Wat Ek Phnom has remained standing for almost a millennium despite earthquakes, monsoon cycles, root intrusion and soil movement. Excavations reveal that Khmer builders created layered laterite platforms beneath the temple, possibly designed to distribute weight across unstable ground. Laterite, an iron-rich tropical soil that hardens when exposed to air, acted almost like a primitive concrete. What shocked researchers was the density and compression of these layers. In some areas, the laterite foundation reached compressive strengths, approaching low-grade modern masonry materials after centuries of natural mineralization. The engineering becomes even more puzzling when compared to other ancient civilizations. Roman builders relied on pozzolanic volcanic concrete capable of resisting seawater for over 2,000 years. The Egyptians built pyramids on stable limestone plateaus to minimize subsidence. But Khmer architects faced one of the worst possible environments for long-term stone construction. Tropical wetlands with intense rainfall exceeding 1,300 millimeters annually. Despite this, the temple's central sanctuary remains relatively aligned. Some structural surveys suggest deviations smaller than a few centimeters across sections several meters wide. An astonishing level of stability for medieval Southeast Asian construction. The stones themselves present another unresolved mystery. Many of the sandstone blocks appear tightly fitted with minimal mortar. Some joints are so narrow that even thin blades struggle to pass between them. Historians traditionally argue that Khmer workers used iron chisels, wooden levers, and manual polishing techniques. But microscopic analysis of certain tool marks suggests repetitive abrasion patterns, more consistent with advanced sanding processes than crude hammering alone. Researchers believe quartz sand mixed with water may have been used as an abrasive cutting compound, similar to techniques proposed for ancient Egyptian granite work. However, recreating the same precision using replicated medieval Khmer tools has proven extremely difficult. Even more mysterious is the transportation problem. Some sandstone blocks used at Wat Ek Phnom weigh several tons and likely originated from quarries located dozens of kilometers away. Moving such stones through floodplains and jungle terrain without wheeled heavy machinery would have required enormous coordination. Scholars estimate that transporting a single large block could have demanded hundreds of labourers using wooden sledges, bamboo rollers, and seasonal waterways. Yet, no surviving Khmer texts explain the logistical systems behind these operations. This absence of documentation has fueled speculation that the Khmer Empire possessed organizational and engineering capabilities far more advanced than traditionally assumed. The carvings at Wat Ek Phnom deepen the mystery further. Many pediments and lintels display highly symmetrical geometric patterns and mythological scenes carved with remarkable consistency. Some decorative grooves are only millimeters deep, yet maintain clean proportions after nearly 1,000 years of erosion. Sandstone is softer than granite, but it fractures easily under uncontrolled pressure. Achieving such detail repeatedly would have required extraordinary control over carving angles and force distribution. Certain historians believe Khmer artisans may have employed proportional measurement systems or reusable geometric templates. If true, this would suggest standardized architectural mathematics operating across multiple Khmer temple sites centuries before modern surveying instruments existed in the region. The climate resistance of the structure is equally difficult to explain. Cambodia's environment is among the harshest in Southeast Asia for preserving exposed stone architecture. High humidity accelerates biological growth, while thermal expansion and acidic rainfall gradually fracture mineral surfaces. Yet many laterite sections at Wat Ek Phnom remain surprisingly durable. Scientific studies on laterite used in Khmer construction found that oxidation of iron compounds over time may create hardened outer shells that naturally protect interior material from rapid decay. In other words, parts of the temple may have slowly strengthened themselves through long-term chemical transformation. This phenomenon has drawn comparisons to Roman marine concrete, which becomes stronger through interaction with seawater crystals over centuries. In both cases, ancient builders may have unintentionally exploited chemical processes modern science only recently began fully understanding. The difference is that Roman engineering texts survived. Khmer engineering methods largely disappeared with the decline of the empire, leaving modern researchers to reconstruct fragmented clues from ruins alone. Another unresolved question involves astronomical alignment. Like many Khmer temples, Wat Ek Phnom appears carefully oriented along cardinal directions. Certain corridors and gateways align closely with solar movement during specific times of the year. Achieving this level of orientation without magnetic compasses or optical instruments would have required repeated long-term sky observations. Researchers studying Khmer architecture found that many temples across Cambodia share remarkably consistent directional patterns over distances spanning hundreds of kilometers. This suggests the existence of a standardized cosmological or astronomical surveying system. Some scholars propose that Khmer architects tracked solar shadows using fixed observation poles and seasonal horizon markers. Others argue that water reflection techniques may have helped establish visual alignment baselines, but no surviving evidence fully explains how large-scale directional accuracy was maintained across generations. The mystery becomes even greater when considering the immense labor coordination required to keep temples aligned despite uneven terrain and shifting foundations. Hydraulic engineering may hold another hidden clue. The Khmer Empire is famous for massive reservoirs and canal systems surrounding Angkor, but smaller regional temples like Wat Ek Phnom were also integrated into sophisticated water management networks. Satellite imaging and ground surveys have identified ancient moats, embankments, and channels surrounding the temple complex. These systems likely served religious symbolism, irrigation control, and flood management simultaneously. Some archaeologists believe Khmer hydraulic infrastructure was so advanced that it allowed dense urban populations to survive seasonal climate extremes for centuries. Yet this same system may have contributed to collapse. Paleoclimate studies indicate Southeast Asia experienced severe megadroughts between the 14th and 15th centuries. Tree ring data and sediment analysis suggest alternating cycles of devastating droughts and extreme monsoon flooding destabilized Khmer water networks. If true, Vatek Phnom may represent not just an engineering achievement, but evidence of how even highly advanced civilizations can become vulnerable when environmental systems exceed their ability to adapt. The temple's decline remains strangely silent. Unlike many ancient cities destroyed by invasion or fire, Vatek Phnom appears to have faded gradually. Jungle growth overtook structures, maintenance ceased, religious centers shifted elsewhere. No massive battlefield debris or widespread burn layers clearly explain abandonment. It was as if the civilization sustaining the monument slowly lost the capacity to preserve it. Do you think the Khmer Empire lost ancient engineering knowledge that modern science still cannot fully explain? Share your thoughts in the comments below.
Hala Sultan Tekke, on the southern coast of Cyprus near modern Larnaca, was one of the wealthiest cities in the ancient Mediterranean. More than 200 years ago, ships arrived here from Egypt, Greece, Anatolia, the Levant, and possibly lands far beyond. Yet many of the technologies that made this vast trading network possible remain unexplained. The site was first identified through archaeological investigations during the 20th century, but major discoveries accelerated after extensive excavations led by researchers from the University of Gothenburg, beginning in the 1970s and continuing into the 21st century. What emerged from the ground was not a small coastal settlement, but a major Bronze Age city covering as much as 25 to 50 hectares, making it one of the largest urban centres known in Cyprus during the Late Bronze Age. The discoveries immediately raised a question: how did a city on an island become one of the most important commercial hubs in the entire Eastern Mediterranean around 1500 to 1150 BC? Archaeologists have uncovered evidence of an astonishing international economy. Imported pottery from Mycenae in Greece, ivory from Africa, precious stones originating in Central Asia, Egyptian artifacts, and luxury goods from the Levant have all been found at the site. Chemical analyses indicate that goods travelled thousands of kilometres before reaching Hala Sultan Tekke, and some materials may have crossed distances exceeding 3,000 kilometres. For comparison, the distance between Cyprus and Egypt is roughly 500 kilometres, while the distance between Cyprus and mainland Greece exceeds 800 kilometres. Yet trade connections linked all of these regions into a single economic system. The mystery is not that trade existed, but the scale on which it operated. Without modern navigation equipment, advanced maps, or centralized communications, merchants somehow coordinated an international trading network comparable in complexity to some later Iron Age economies. Researchers still debate how information moved efficiently enough to sustain such extensive commercial activity. Cyprus was the primary source of copper for much of the Eastern Mediterranean during the Bronze Age. In fact, many historians believe the name Cyprus itself became closely associated with copper production. Large oxide-shaped copper ingots recovered from shipwrecks, such as the famous Uluburun shipwreck, demonstrate the enormous scale of Bronze Age metal trade, with some ingots weighing around 25 kilograms each. Thousands of such ingots circulated across Mediterranean trade routes. Producing this volume of copper required mining, transportation, smelting, quality control, and distribution systems operating with remarkable efficiency. Yet archaeologists still struggle to reconstruct the complete industrial infrastructure behind this production. Questions remain about how temperatures exceeding 100 degrees Celsius were maintained consistently in Bronze Age furnaces, how ore quality was standardized, and how production was organized without modern industrial management. The archaeological evidence suggests a sophisticated metallurgical economy, but many of the technical details remain unknown. A city engaged in international commerce should leave behind extensive administrative records. Ancient Egypt produced written archives. The Hittites produced thousands of clay tablets, and Mesopotamian cities generated entire libraries of economic records. Hala Sultan Teki, however, presents a puzzle. The city clearly managed warehouses, imported luxury goods, industrial production, and maritime trade, yet very little evidence survives explaining how these activities were coordinated. Who controlled trade agreements? Who organized shipping schedules? Who tracked incoming and outgoing cargo? The economic system appears highly sophisticated, but much of its administrative structure remains invisible. Excavations reveal carefully organized residential districts, workshops, storage facilities, and industrial zones. This was not random growth. City appears planned. Road systems connected different sectors. Specialized production areas were separated from living spaces, and large storage facilities indicate centralized management of valuable goods. Researchers estimate that several thousand people may have lived here during its peak. Compared with many contemporary settlements across Europe, Hala Sultan Teke exhibited a level of urban organization more comparable to major cities of the Near East. How such planning knowledge developed and spread across the Bronze Age Mediterranean remains uncertain. Every major city depends on water, and this simple fact creates another mystery. Southern Cyprus experiences long dry seasons, meaning that sustaining a large population, industrial production, livestock, and visiting merchants required dependable water supplies. Yet the complete hydraulic system remains poorly understood. Some scholars suggest wells and groundwater sources played a major role, while others believe water collection and storage systems were more sophisticated than currently recognized. The city survived for centuries, indicating that its inhabitants solved a difficult environmental challenge, but exactly how they achieved this remains debated. This may be the greatest mystery of all. Nothing about Hala Sultan Teki makes sense unless its inhabitants mastered the sea. The city's wealth depended on ships, its copper exports depended on ships, its imported luxury goods depended on ships, and ultimately its survival depended on ships. Yet almost none of those ships survive. Wood decays, ropes disappear, sails vanish, and the technology that connected entire civilizations has largely been erased by time. Archaeologists can estimate trade routes, but reconstructing the ships themselves is far more difficult. The Uluburun shipwreck, discovered off the coast of Turkey and dating to around 1300 BC, offers one of the few surviving glimpses into Bronze Age maritime technology. The vessel carried more than 10 tons of cargo, including copper ingots, tin ingots, glass, ivory, jewelry, and luxury goods. Its existence demonstrates that late Bronze Age ships could transport enormous loads across open water. But this raises a larger question. How did sailors navigate? The Gamadi compass would not appear for centuries. Accurate nautical charts did not exist, and there were no lighthouses across the Mediterranean guiding vessels from port to port. Yet ships repeatedly crossed hundreds or even thousands of kilometers. Some researchers believe sailors navigated using stars, prevailing winds, seasonal weather patterns, ocean swells, and detailed mental maps passed down through generations. Others argue that Bronze Age mariners possessed levels of practical astronomical knowledge that modern historians still underestimate. Another mystery concerns ship construction itself. Bronze Age shipbuilders created vessels capable of carrying cargo weighing many tons while surviving storms, waves, and long-distance voyages. The engineering challenge was immense. A vessel carrying 10 tons of copper could easily sink if weight distribution was poorly managed. Hull strength, buoyancy, sail design, and cargo arrangement all required sophisticated knowledge. Unlike monumental architecture, which survives for millennia, shipbuilding technology leaves very little evidence behind. As a result, one of humanity's most important technological achievements may also be one of its least understood. Without these ships, Hala Sultan Tekke could never have become a major international port. Yet the methods that made such maritime success possible remain largely hidden beneath the sea. Around 1200 BC, the Bronze Age world experienced one of history's greatest collapses. Major powers declined, trade routes fragmented, cities were destroyed, and entire kingdoms disappeared. Hala Sultan Tekke was caught in this crisis. Evidence suggests the city was eventually abandoned as the wider Eastern Mediterranean trading system unraveled. The causes remain controversial. Earthquakes, drought, warfare, political instability, economic collapse, and the movements of the mysterious sea peoples have all been proposed. No single explanation fully accounts for the evidence. The city that once connected continents simply faded from history. If the shipbuilders of Hala Sultan Tekke could cross the Mediterranean without modern technology, what other ancient engineering secrets have been lost forever?
The Udayagiri Buddhist complex is hidden among the low hills of Odisha in eastern India. At first glance, it appears to be another forgotten Buddhist ruin. Yet beneath layers of earth that concealed it for centuries lies one of the most remarkable engineering puzzles in ancient South Asia. Archaeologists uncovered evidence of vast monasteries, sophisticated drainage systems, enormous stone sculptures, and construction techniques that continue to raise questions today. The mystery is not who built Udayagiri. Historians generally agree that the complex flourished between the 7th and 13th centuries CE under powerful Buddhist patronage. The real mystery is how ancient builders, working without modern surveying equipment, steel machinery, reinforced concrete, or written engineering manuals, created a massive hilltop complex whose technical achievements remain only partially understood. The modern rediscovery of Udayagiri occurred through archaeological investigations conducted during the 20th century, particularly large-scale excavations by the Archaeological Survey of India, beginning in the 1980s. What researchers initially expected to be a modest Buddhist site soon revealed itself as a sprawling monastic centre, covering multiple terraces across a hill landscape. Excavations uncovered large monasteries, shrines, stupas, sculptural workshops, residential areas, and hundreds of artifacts. As the layers of soil were removed, an unexpected picture emerged. Udayagiri was not simply a religious centre, it was an enormous engineering project. One of the first puzzles concerns planning. Modern engineers know that constructing large complexes on uneven terrain requires careful topographical analysis. Today, this would involve satellite mapping, digital elevation models, laser measurements, and structural calculations. Yet, the builders of Udayagiri transformed an irregular hill into a sequence of interconnected architectural platforms with astonishing precision. Large monasteries were positioned on level terraces while maintaining alignment with surrounding structures. Pathways, staircases, and ceremonial routes connected different elevations without disrupting the overall organization of the complex. Archaeologists have identified evidence that substantial portions of the hillside were reshaped before major construction began. This implies large-scale earth-moving operations whose logistics remain difficult to reconstruct. Unlike the Romans, who left extensive engineering texts, the builders of Udayagiri left virtually no technical documentation explaining how these calculations were performed. The challenge becomes even more impressive when considering climate. Odisha experiences intense monsoon rainfall. In some modern years, annual precipitation exceeds 1,500 millimeters.
Water is one of the greatest enemies of ancient architecture, especially on slopes where runoff accelerates erosion. Yet many structures at Udayagiri survived for centuries before burial. Excavations revealed evidence of sophisticated drainage planning integrated directly into the architecture. Channels directed water away from foundations. Slopes appear to have been designed to control runoff. Retaining walls stabilized vulnerable sections of terrain. Modern geotechnical engineers understand that poor drainage can destroy even contemporary buildings. The fact that Udayagiri remained functional for hundreds of years suggests that its builders possessed practical hydrological knowledge far beyond what many assume for medieval South Asia. Perhaps the most intriguing mystery involves the bricks themselves. Throughout the site, archaeologists encountered bricks displaying remarkable durability, despite surviving centuries of monsoon exposure, temperature fluctuations, biological growth, and burial beneath heavy layers of sediment. Under normal conditions, ancient brick structures gradually deteriorate through cycles of moisture penetration, salt crystallization, thermal stress, and mechanical erosion. Yet many bricks recovered from Udayagiri retained sharp edges, structural integrity, and surprising uniformity. Their resilience has become one of the site's most fascinating engineering questions. Scientific analysis of ancient bricks elsewhere in India has demonstrated that durability depends on numerous variables, including clay composition, mineral content, firing temperature, kiln atmosphere, and manufacturing consistency. Even small differences can dramatically affect longevity. Modern industrial brick production relies on carefully controlled temperatures, often exceeding 900 to 1000 degrees Celsius. Achieving comparable consistency using ancient technologies would have required extraordinary expertise. Researchers suspect that Udayagiri's builders possessed highly refined knowledge of local clay sources and firing techniques. The uniformity observed in many surviving bricks suggests standardization rather than random production. Some scholars compare this achievement to the famous brick technologies of the Indus Valley civilization, where standardized brick ratios were maintained across vast distances more than 2,000 years earlier. Yet, unlike modern factories, the workshops that supplied Udayagiri left behind few clues explaining how such consistency was achieved. The durability of these bricks becomes even more impressive when compared with other historical sites. Many medieval brick structures across tropical Asia have suffered severe deterioration due to moisture and vegetation. Portions of ancient monasteries at Nalanda required extensive conservation after centuries of exposure. Numerous brick monuments in Southeast Asia have undergone repeated restoration campaigns. Udayagiri's surviving materials demonstrate resistance that appears disproportionate to their age and environmental conditions. Scientists continue to investigate whether unique mineral compositions, specialized firing techniques, or construction methods contributed to this longevity. No definitive explanation has yet emerged. Another mystery surrounds transportation. The site contains large stone sculptures, architectural blocks, decorative elements, and massive carved images of the Buddha and Bodhisattvas. Some individual pieces weigh several tons. Transporting such materials across uneven terrain remains difficult even today. Modern construction projects rely on cranes, trucks, hydraulic systems, and engineered roads. Medieval builders possessed none of these advantages. Archaeologists believe workers likely used combinations of earthen ramps, rollers, ropes, wooden sledges, and coordinated labor forces. However, direct evidence remains scarce. Similar questions surround the construction of Borobudur in Indonesia, Angkor in Cambodia, and Machu Picchu in Peru. In each case, Researchers understand the final result but continue debating the precise logistical methods that made it possible. The sculptural program of Udayagiri introduces another technical puzzle. The site contains some of the finest Buddhist carvings in eastern India. Many statues exhibit remarkable proportional consistency, despite being produced across different periods. Facial dimensions, body ratios, ornamental details, and symbolic features often follow strict patterns. This suggests the existence of standardized design systems. Ancient craftsmen may have used geometric grids, measurement canons, or mathematical formulas similar to those employed in classical Greek sculpture and traditional Indian architectural treatises. Yet, the practical methods used to transfer these designs from concept to finished monument remain uncertain. The precision achieved by artisans working with simple tools continues to impress modern researchers. Researchers have also explored possible astronomical considerations in the site's layout. While evidence remains debated, certain architectural alignments appear too deliberate to dismiss entirely. Across the ancient world, major ceremonial centers often incorporated astronomical observations into their design. Examples include Stonehenge in Britain, Chichen Itza in Mexico, and Angkor Wat in Cambodia. Whether Udayagiri participated in a similar tradition remains unresolved. Nevertheless, the possibility suggests a level of planning that extended beyond architecture into environmental observation and celestial knowledge.
Termessos rises more than 1,000 meters above sea level inside the Taurus Mountains near modern Antalya in southwestern Turkey, where an entire ancient city still clings to steep limestone slopes that geology suggests should have become progressively unstable long ago. Unlike many ancient mountain settlements that vanished beneath landslides or dense vegetation, Termessos was never completely forgotten, but its remarkable engineering was only properly understood after systematic archaeological surveys during the 20th century, followed by geological mapping, laser scanning, structural analysis, and detailed studies within Guluk Mountain National Park. Founded by the Pisidians and flourishing from at least the 4th century BCE before later becoming part of the Hellenistic and Roman worlds, the city occupies an elevation of roughly 1,000 to 1,200 meters across an exceptionally rugged karst landscape. Ancient writers, including Arrian, recorded that even Alexander the Great abandoned plans to capture the city in 333 BCE because its natural defenses made a direct assault almost impossible. Yet the military reputation of Termessos is only part of a much deeper mystery. The greater question is how an entire urban center was successfully constructed on terrain that modern engineers would normally regard as one of the least favorable places for large-scale permanent architecture. Every surviving structure seems to demonstrate an extraordinary understanding of the mountain itself, rather than an attempt to overpower it. Instead of leveling the landscape, the builders carved enormous terraces directly into fractured limestone, allowing each major public building to rest upon carefully selected sections of exposed bedrock. Modern geological investigations show that the Taurus Mountains consist largely of heavily jointed Mesozoic limestone, affected by tectonic uplift, solution cavities, and countless natural fractures. Such terrain normally creates significant instability because water penetrates cracks, gradually enlarges voids through chemical weathering, and weakens entire rock masses over centuries. Constructing a city weighing many thousands of tons across these conditions without triggering progressive slope failure would require detailed knowledge of rock stability. Yet no surviving inscriptions, engineering manuals, or construction records explain how the Pisidians identified which parts of the mountain could safely support temples, marketplaces, houses, reservoirs, and defensive walls. Even today, geotechnical engineers rely upon drilling, seismic surveys, and laboratory testing before approving large projects on comparable slopes, whereas the ancient builders somehow reached remarkably accurate decisions using techniques that remain undocumented. This unexplained precision becomes even more striking inside the theatre, perhaps the most dramatic monument at Termessos. Rather than occupying a broad plateau, the theatre sits directly against the mountainside while overlooking distant valleys far below. Much of its seating depends upon the natural rock instead of massive artificial substructures, reducing weight while allowing the mountain itself to carry the greatest structural loads. Although earthquakes have repeatedly affected southwestern Anatolia throughout recorded history, numerous seating rows remain closely aligned after more than 2,000 years. Structural researchers have suggested that selecting exceptionally competent rock masses instead of merely convenient locations may have been one of the city's greatest engineering achievements. But no one knows how such assessments were consistently made across the entire settlement without modern geological instruments. The more archaeologists examine the city's layout, the more its retaining systems challenge conventional expectations. Nearly every major terrace depends upon stone retaining walls, holding back enormous volumes of soil and rock on steep inclines, where gravity constantly attempts to pull everything downhill. Ordinarily, retaining walls gradually fail because rainwater accumulates behind them, increasing hydrostatic pressure until the masonry bulges or collapses. Yet many of Termessos' terrace walls remain standing after more than 20 centuries, despite continuous seasonal rainfall, winter freeze-thaw cycles, tree root expansion, and repeated seismic activity. Excavations have revealed carefully positioned drainage channels, stone-lined outlets, and subtle gradients that appear designed to remove infiltrating water before dangerous pressure could develop. Some specialists believe much of the drainage network remains buried beneath accumulated sediments, meaning the city may still conceal an integrated hydraulic system that has never been fully mapped. Water management presents another puzzle because the mountain offers no major river capable of sustaining a large permanent population. Instead of depending upon abundant natural springs, the inhabitants constructed numerous cisterns carved directly into bedrock, many coated with waterproof hydraulic mortar, whose exact performance continues to attract scientific attention. Rainwater flowing naturally across the mountain appears to have been intercepted, filtered, and stored with remarkable efficiency. Laboratory analysis has shown that several surviving waterproof mortars contain carefully proportioned mixtures of lime, crushed ceramics, and mineral aggregates capable of resisting water penetration for extraordinarily long periods. Although similar hydraulic technologies were known elsewhere in the ancient Mediterranean, archaeologists still debate how builders working in such an isolated mountain environment consistently produced durable reservoirs capable of surviving centuries of climatic extremes without widespread structural failure. Even the streets contribute to the engineering mystery. Rather than forcing straight avenues across impossible gradients, the urban plan follows the mountain's natural contours with subtle adjustments that minimize excavation while reducing long-term erosion. Modern topographic surveys indicate that many roads, stairways, and public spaces align with naturally stable ridges instead of crossing zones more susceptible to collapse. This suggests the city's planners possessed an unusually sophisticated understanding of terrain stability, achieved entirely through observation and practical experience. Their choices reduced the need for excessive retaining structures, while distributing structural loads across stronger portions of the landscape, creating a settlement that appears almost woven into the mountain rather than simply placed upon it. Time itself should have finished what gravity could not. Southwestern Turkey lies within a tectonically active region influenced by the complex interaction of the African, Arabian, and Anatolian plates, and historical records describe destructive earthquakes affecting nearby cities across many centuries. Geological weathering continuously enlarges fractures within limestone, while freeze-thaw expansion gradually widens existing cracks and weakens exposed rock surfaces. Under such conditions, large mountain settlements usually experience progressive deformation, collapsing terraces, displaced foundations, and widespread structural instability. Yet substantial portions of Termessos continue to occupy their original positions with surprising integrity. Although some buildings undoubtedly suffered damage and parts of the city were eventually abandoned, the overall urban framework still demonstrates a level of resilience that appears disproportionate to the hostile geological environment in which it was created.
Lalitgiri, isolated on a low hill range in Odisha, eastern India, appears at first glance to be another ruined Buddhist monastery. Yet beneath its weathered bricks lies one of the most puzzling engineering stories in ancient South Asia. Archaeologists uncovered evidence of a major Buddhist center dating from roughly the 1st century BC to the 13th century AD, making Lalitgiri one of the oldest Buddhist complexes in India. What transformed the site from an ordinary excavation into an archaeological mystery was not merely its age, but the discovery of advanced construction techniques, unusually durable materials, sophisticated planning, and perhaps most intriguingly, a series of stone relic caskets crafted with a level of precision that continues to raise questions about the technological capabilities of the people who built them. The modern rediscovery of Lalitgiri began during archaeological surveys of Odisha in the 20th century. Systematic excavations conducted by the Archaeological Survey of India eventually revealed a massive monastic complex, a large brick stupa, dozens of smaller votive stupas, sculptures, inscriptions, and one of the most important finds ever made at a Buddhist site in India. A relic chamber containing nested stone containers believed by some scholars to have held sacred Buddhist relics. As excavation expanded, researchers realized that Lalitgiri was not an isolated monastery. It formed part of a vast Buddhist network together with Ratnagiri and Udayagiri, creating a regional religious and educational landscape that flourished for centuries. Yet every new discovery seemed to generate even more difficult questions. The first puzzle emerges from the location itself. Lalitgiri occupies elevated terrain overlooking the surrounding plains. Modern visitors can reach the hill with relative ease, but transporting construction materials there nearly 2,000 years ago would have been a very different challenge. Archaeologists estimate that the principal stupa and associated structures required hundreds of thousands of bricks. Even if each brick weighed only 2 to 4 kilograms, the total mass of material transported uphill would have reached hundreds or even thousands of tons. Similar logistical challenges have been documented at sites such as Nalanda and Sanchi, but Lalitgiri presents an additional complication. Evidence suggests multiple phases of expansion over several centuries, meaning construction was not a single event but a continuous process requiring stable supply chains, labor organization, and engineering knowledge. No written records survive to explain how this logistical system operated. The durability of the brickwork presents another mystery. Many ancient brick structures across tropical South Asia have suffered severe deterioration from monsoon rains, biological growth, thermal stress and erosion. Yet substantial portions of Lalitgiri survived for more than a millennium. Laboratory analysis of ancient Indian bricks has demonstrated compressive strengths that sometimes approach or exceed those of certain modern fired bricks. Researchers believe ancient craftsmen carefully selected clay sources and controlled firing temperatures, but the exact production methods remain uncertain. Unlike modern brick manufacturing, which relies on standardized industrial kilns and temperature monitoring systems,
ancient builders achieved remarkable consistency using technologies that remain only partially understood. The survival of these structures becomes even more impressive when compared with many later medieval buildings that deteriorated more rapidly despite having access to more advanced tools. Water management may represent an even greater engineering achievement. Odisha receives significant seasonal rainfall, often exceeding 1,400 millimeters annually. Any large hilltop complex exposed to centuries of monsoon activity faces constant threats from runoff, erosion, and foundation instability. Modern engineers combat such problems using drainage calculations, hydrological models, and reinforced foundations. Lalitgiri's builders possessed none of these technologies, yet the archaeological record indicates that the site remained functional through countless monsoon cycles. Excavations have identified drainage channels and evidence of carefully planned water control systems, but researchers still struggle to reconstruct the complete hydraulic network. The unanswered question is whether surviving features represent only a small fraction of a much larger engineering system that has since disappeared. The mystery becomes deeper when examining the broader architectural planning of the complex. The layout of monasteries, shrines, pathways, and stupas suggests deliberate organization rather than gradual random growth. Ancient builders appear to have balanced religious symbolism with practical concerns such as circulation, visibility, drainage, and structural stability. Comparable planning can be observed at major Buddhist centers like Nalanda, yet Lalitgiri's elevated terrain imposed additional constraints. Modern archaeological mapping reveals alignments and spatial relationships that imply careful surveying methods. The challenge is understanding how such measurements were performed. Without modern optical instruments, laser levels, or standardized engineering equipment, ancient surveyors still managed to create a coherent architectural landscape capable of functioning for centuries. Among all these mysteries, however, none is more fascinating than the relic caskets discovered within the stupa complex. These objects transformed Lalitgiri from an important archaeological site into a genuine technological puzzle. The relic chamber contained multiple nested containers fashioned from stone with remarkable craftsmanship. At first glance, the caskets appear simple. Closer examination reveals an extraordinary degree of precision. The surfaces were carefully shaped and smoothed. The lids fit their bases with striking accuracy. Symmetry is maintained across multiple components. Internal cavities were hollowed with controlled dimensions while preserving structural integrity. Even more remarkable, these achievements were accomplished using technologies available nearly 2,000 years ago. To appreciate the challenge, it is useful to compare the relic caskets with other ancient precision stonework. Egyptian craftsmen produced finely finished granite sarcophagi. Roman artisans carved marble sculptures with astonishing detail. Indian stoneworkers created the polished pillars of Emperor Ashoka and the rock-cut architecture of Ajanta and Ellora. Yet each of these projects required highly specialized knowledge, sophisticated toolkits, and generations of accumulated expertise. The relic caskets of Lalitgiri belong within this broader tradition of precision craftsmanship, but their existence raises a difficult question. Why invest such extraordinary effort into objects that would remain hidden inside a sealed stupa? Microscopic examination suggests controlled shaping and finishing techniques that required exceptional skill. Stone is an unforgiving material. Remove too much and the piece is ruined. Apply uneven force and fractures can develop. Achieve symmetry on one surface but not another, and the final object becomes visibly imperfect. Modern machinists solve these problems with calibrated tools and measurement devices. Ancient artisans relied on experience, templates, abrasives, and techniques that remain poorly documented.
The finished caskets demonstrate not only artistic ability, but also a practical understanding of geometry, material behavior, and manufacturing control. The nested arrangement of the containers introduces another layer of complexity. Multiple vessels were designed to fit within one another while maintaining dimensional compatibility. This implies planning before fabrication began. Each container had to be produced according to measurements that allowed the complete assembly to function as intended. Similar engineering logic appears in modern precision manufacturing, where components must meet predetermined tolerances. Whether ancient craftsmen thought in terms comparable to modern tolerances remains unknown, yet the physical evidence suggests they achieved remarkably accurate results. The mystery goes beyond craftsmanship. Creating these relic caskets required skilled artisans, training systems, workshops, tools, and resources. While the finished objects remain, the knowledge and infrastructure behind them disappeared centuries ago.